Yes. Thanks for joining.
Oh, thank you for organizing.
Captain Hong.
Captain Hong.
Morning, Boris.
Hey, guys.
Hey, how are you?
Good, you?
Nice. Just wake up. Sorry about that.
Yeah. So for me, it's middle night. Not yet.
Okay,
Will
that's even
become
more difficult.
middle night soon. Yeah. Hi, Daniel.
Hi, everyone.
Hello, hi.
Hello, hi.
Welcome.
Thank you for organizing it.
May I have a question?
Yeah, sure.
So how would the Q&A session works? Like after the talk and people can send some question in the chat or in text and I answer the question, so or what?
Yes, so the question and answer periods, they are moderated by the chairs. And then you can write your question through the chat, or you can write your question over Twitter.
Okay.
Or you can ask them directly if you have, Sasha, does the audience have the permission to turn on their videos? No, huh?
No.
I think it's
Then
just
how would
like,
the speaker...
just the chairs. The chairs will just tell you the questions as they come up on the chat and in Twitter as we go along.
Wait, so Daniel and I are supposed to monitor Twitter?
No, we can. I'll message you any questions that come off Twitter.
Oh, okay.
So you can possibly add them, but otherwise just keep an eye on the chat and pass those on. So we just have the chairs directly asking the questions to the speakers rather than having like many voices going on.
Yeah.
But yeah, I'll send messages to the chairs if any questions come up on Twitter that could be of interest.
So we're gonna all be like automatically muted, right, during the workshop?
Yes.
Yeah.
Oh, I see.
Okay, I'm going to start now.
Sasha, I think there's no sound. Hello and welcome everyone to our OHBM satellite meeting on gradients in brain organization. My name is Boris Bernhard and I'm researcher at the Montreal Neurological Institute, and I'm very excited to introduce this workshop to you today. Before we get started, I would like to ask you to mute your microphones, please, and to turn off your video so that we don't interfere with the broadcasting of the conference program. Thank you very much. As you may know, this workshop was originally planned as an in-person meeting, However, in light of the COVID-19 pandemic, we decided to move this workshop to a virtual format. And I would, for this, like to thank the members of the organizing committee for helping with this and for being really instrumental for making this workshop possible and also transforming it. Dani Margulies, Casey Pacola, Thomas Yu, Richard Bethlehem, Sophie Falk, Johnny Smallwood, Beth Jeffries, and Julien Doyon. Thank you very much for your help. And special thanks also go to Debbie Rashowski and Sasha Kelly from the Neuro Events team who were instrumental in the event logistics. Thank you all. We would also like to thank our partners who generously supported the workshop, the Montreal Neurological Institute, the Quebec Bioimaging Network, Cuban, the McGill Faculty of Medicine, and CNRS from Paris, who generously supported this workshop. Thank you. Last but not least, I would also like to thank all the outstanding speakers who kindly agreed to speak at this workshop and to share their work with us. And they were also very flexible in transforming their talks that were originally planned as traditional talks to move them to a virtual format, and they sent us their talks on time. So special thanks to all of them, and I'm really looking forward to hearing them talk and to the discussions that will follow. Our workshop will have the broad theme of cortical gradients, and we will cover methodological aspects, look at how brain organization, gradual brain organization and cognition interact, and we will look at evolutionary and developmental principles of cortical gradients. Our workshop day is quite dense. However, I hope it's going to be very enriching and entertaining. We'll have 3 scientific sessions. The first session will be chaired by Thomas Yu and Dani Margulies on gradient methods, both from an introductory perspective as well as from a real cutting edge perspective on gradient analytics. The second session, which will be chaired by Beth Jeffries and Johnny Smallwood, will focus on how gradients may relate to cognitive operations in humans. And the third session will look at evolutionary and developmental aspects of cortical gradients, and that session will be chaired by Casey Pacola and Richard Bethlehem. Due to the virtual format and due to trying to condense the theme, we were able to show this workshop at different continents. This, however, comes at the cost that the breaks are relatively short. So you can take advantage of the breaks to either step away from gradients for a little while, or you can stay with us and engage in hopefully fun and entertaining activities that we've planned for the 2 short breaks. During the workshop, as I mentioned already before, please try to keep your microphones muted and keep your videos off. After each talk, the chairs will moderate a short question and answer period. And at the end of each session, if we have time, there will also be an overall question and answer period, during which you can then turn your video back on and you can ask questions directly to the speakers. You can also engage with the speakers after the talk through the chat, or you can engage with the entire workshop and the speakers through social media. And I've just shown the Twitter handle here. So we'll try to tweet about each of the talks on Twitter, and hopefully we get some kind of community response. We'll also facilitate the streaming of the workshop to people who are not registered to the workshop because the registration was full. And this will happen through YouTube. So if ever you should experience some technical difficulties on the Zoom call, feel free to also check out the YouTube channel. So with this, I would like to thank everybody again to help making this workshop possible. And I would now like to pass the baton to Dani Margulies and Thomas Yu, who are the chairs of the first session. Thank you all.
Hi. Hi, Thomas.
Hi. I guess we are going to start. This is a bit awkward.
Well, no, but yes, I've got a joke to start that off. Hey, Thomas. What did Broadman Area 39 say to its neighbor when it realized it was coming down with a bad case of gradient fever?
I don't know.
Hey, 40, I'm not feeling so sharp. Thanks, Thomas.
Pretty good. That's pretty good. Yes.
Well, it is what it is. Welcome to session 1 of to session 1 of the Gradients workshop. We have 4 fantastic speakers today that we're very excited about. Thomas, take it away.
Yes, so I'm going to introduce the first speaker. The first speaker is Ye Tian from University of Melbourne. Ye Tian graduated with a Bachelor of Medicine in 2013 from Sichuan University, and then completed training in psychiatry at Peking University in China. She then did a PhD at the University of Melbourne with Australia. I think she just graduated. Is that right? Yeah, you just graduated and you're going to start a postdoc with...
Not yet graduate yet. I just submitted my thesis maybe 3 weeks ago. So my PhD thesis hasn't been passed yet. I'm still waiting.
Well, I guess you can treat this as like a thesis defense then.
Yeah. Thanks.
Anyway, without further ado, Ye Tian is, let's go ahead. Someone's going to start the video, is that right?
Higher order, higher association, high order association. Hi everyone, I'm Ye Tian from the University of Melbourne in Australia. I'm very glad today that I'm here to chat with everyone about the 2 most commonly used models in representing brain organization, the smooth gradients and discrete regions, or a bit of both. Okay, let's start. So the brain organization has been studied for over a century. We believe that the structure, function, and connectivity of the brain are topographically organized like a map, in contrast to a diffused or random phenomenon. So classic models of brain topography parcellate the brain into distinct partitions with discrete boundaries, while recent studies of cortical gradients suggest that the topographic variation in brain structure, function, and connectivity might be better conceptualized in terms of continuous gradients of gradual change in the absence of discrete boundaries. So this new idea challenges the traditional notion of brain organization and gives rise to the contention about whether the brain is organized into distinct partitions or continuous gradients. So here are the 2 models of brain topography. One suggests distinct cortical patches. One suggests continuous gradients of gradual change. So are the 2 models contradictory? Can we somehow reconcile these 2 models of brain topography to represent the brain organization? So of course, on one hand, we can continuously characterize the spatial variation in brain structure, function, and connectivity across the topography. On the other hand, we should also be able to delineate a hard boundary when the spatial variation is significantly large. So how large or how significant the spatial variation must be to warrant such a hard boundary? We conceptualize such a question as mode selection in our work. So in today's talk, I will briefly introduce principled approaches to reconcile these 2 complementary models of brain topography. In particular, I will introduce the idea of mode selection in the context of gradient mapping in 2 brain areas. One is the insular cortex and another one is the subcortex. So here is the insular cortex. The insular cortex is traditionally and most commonly categorized and parcellated into distinct subregions. Each subregion presumably represents distinct patterns of structure, function, or connectivity. However, as you can see the few examples I show here, the number of insular subregions and the subregional borders differ substantially across different parcellation studies and parcellations. And the modalities, sorry. So to understand the high inconsistency, we systematically evaluated traditional clustering approaches in insular parcellation and the new models of continuous gradients. So we found that the topographic variation in insular functional connectivity is actually best represented as a continuum along an anterior-posterior axis. So as you can see here, the connectivity, the functional connectivity profile varies at a relatively constant rate from the posterior to anterior, while the slope changes a little bit at breakpoint 1 and 2. The evidence of indicating a sharp boundary in this continuum is relatively weak. So this may in turn suggest or explain the high discordance in the number of insular subregions that previously reported. And moreover, so this continuum is also consistent across several imaging modalities, and early work of track tracing in non-human primates. It also suggests the structural function convergence in the insular topography. So now how about the subcortex? We have categorized that the insular topography is best represented as a continuum. So I now want to apply the model selection framework to investigate the subcortex. The subcortex comprises multiple structures and are widely implicated in the pathology of many neuropsychiatric disorders. However, many of the structures have been studied in isolation without first establishing the functional boundaries between them. The very few existing connectivity-based subcortical atlases, including more than one subcortical nuclei, generally do not preserve such anatomical boundaries. So to understand whether this is a structure-function divergence, in contrast to the convergent phenomenon as we just see in the insular cortex, we use the idea of cortical gradients to continuously map the spatial variation in functional connectivity across the topography of the entire subcortex. So the idea is that we would only delineate a boundary when the spatial variation is significant and is justified by the model selection process. So before I move on to show you the results, I would like to provide a brief overview of how connectivity gradients are typically mapped, given that it is a relatively new concept in this field. I will describe in the mapping in terms of the functional connectivity in the subcortex. So here I show that we first map the functional connectivity between each subcortical voxel and all the other gray matter voxels in the brain. And then we quantify the similarity in the connectivity profile, in the whole brain connectivity profile between each pair of subcortical voxels. So here, instead of using the traditional clustering approaches to group voxels into distinct clusters, as traditional parcellation would do, we decompose the high dimension similarity matrix into a few low dimensions using one of the eigendecomposition methods. So the method we use is called Laplacian eigenmaps, and each of the resulted eigenvector represents a dimension of connectivity difference in the subcortex. Those eigenvectors are typically and normally ordered accordingly. So the first eigenvector or the first gradient explain the most variance, while the second explain the second most variance, etc. So to simplify the explanation, today I would only focus on the first connectivity gradient, which explains the most dominant connectivity difference across the topography of the subcortex. So here we have the eigenmap, the dominant gradient map. So we want to further categorize the connectivity gradient. We developed a technique called gradientography. Let's see how it works. So based on the eigenmap, we then estimate the gradient orientation for each subcortical voxel in the eigenmap, such that we can fit a tensor into the gradient, into the gradient field. Why we need tensor? So after we fit tensor, the shape along the long axis of each tensor represent the direction of the gradient, whereas the gradient magnitude is categorized by the length of the tensor. What we can do then, so as long as we have the tensor, what we can do is to propagate millions of streamlines in this tensor field in a similar way as white matter tractography is typically performed in diffusion imaging. But here we propose the tractography that is based on the connectivity gradients. So we call that gradientography. Let's have a look. So those string propagate, let's have a look at those propagated string lines. Each string line represents a trajectory of maximum change in the eigen map. So here we color the string lines based on the gradient magnitude of each subcortical voxel. Locations with this kind of circumscribed bands here, here, or here indicate the local maximum in the gradient magnitude, which suggests a sharp transition in the connectivity and also in turn suggests the functional boundaries. So the idea of gradientography enables not only a striking visualization of the brain gradients, but also the identification of sharp transition, which is the functional boundary. So let's take a closer look. Here are the string lines that are traveling along the basal ganglia, and we can see transitions between globus pallidus, putamen, nucleus cumbens, and the caudate. We can then parameterize such transitions in a two-dimensional space, which is the idea of diversity curves. And we can see the three transitions, the peaks in the diversity curves that corresponding to the locations of the transitions. Similarly, we can do the same thing for the ventral part, and we see that the string lines that go through the left-right thalamus, hippocampus, and amygdala. Similarly, so more local peaks are noticed in the ventral part of the diversity curves. So now the question is, shall we consider all the peaks? To what extent the peaks or the transition is driven by the matter of chance or other confounds, such as the extent of spatial smoothing during the fMRI preprocessing and also the geometric contraction in the subcortex. So to control those factors, we generated a null model as a gray curve shown here. So the idea is that we parcellate the subcortex at locations when the empirical null empirical peaks are significantly larger than the peaks in the are significantly larger than the null curve, such that the null model can be rejected. Otherwise, we argue that the topographic variation in functional connectivity is best represented as a continuum in the absence of discrete boundary. So this model selection process yielded an initial parcellation for the subcortex with 8 bilateral, comprising 8 bilateral regions, recapitulating a well-known anatomical boundary, anatomical nuclei. So it will be 16 in total, left and right. We then map the connectivity gradient for each of the 16 regions with the performing of model selection recursively. This yielded a hierarchical or multi-scale subcortical parcellation that comprised of 4 organizational scales. But it's not, well, I want to say that it's not all the subcortical regions comprise 4 scales. As you can see here, the globus pallidus or the amygdala only comprise 2 scales. In contrast, hippocampus and thalamus extend further into scale 4. And this is consistent, so we think that this is consistent with the greater functional and organizational complexity in the hippocampus and thalamus compared to the more specific role of globus pallidus in the movement control, regulation of movement control. So this multi-scale subcortical atlas is free to download. I'll show the link later. And this atlas has been utilized in ongoing clinical trials of brain stimulation like TMS and DBS in the treatment of patients with neuropsychiatric disorders, which is very promising. And this slide, I want to show some result that is a little bit beyond the scope of today's talk, but it's quite interesting, so I would like to share. So far, we have only investigated the functional connectivity gradients at rest. So we are wondering whether the connectivity gradients reconfigures in response to changing cognitive demands and task-induced conditions. So to answer this question, we mapped the diversity curves for 7 task fMRI conditions, including, as you can see here, emotion recognition, gambling, language, modal execution, relational, social influence, and working memory. So those two curves, the red and the black, are mapped from the resting state, whereas the other seven curves were mapped from the task fMRI data. So indeed, we found that the subcortical topography shows reconfiguration in all 7 tasks compared to the rest, as you can see here. So in particular, during the task conditions, as I pointed, the anterior putamen integrated more extensively with caudate and nucleus accumbens that are associated with higher order association, high order cognition. In contrast, when we look at the ventral part, the hippocampus segregated more along its longitudinal axis, yielding a more integrated anterior hippocampal amygdala system for emotional, maybe have served better for emotional regulation, and more integrated posterior thalamus that may have benefited learning and spatial memory. So this dynamic reconfiguration may actually reflect a process of neural recruitment into specific functional processing systems, so to cope with those external complex cognitive demands. So to wrap it up, we propose a model selection framework. So this framework can reconcile these two representations of brain topography. It enables the disambiguous, or we disambiguate smooth connectivity gradients from discrete area boundaries. So we show evidence required so the insular cortex, the functional connectivity topography of the insular cortex is best represented as a continuum in contrast to distinct puzzles, whereas the subcortex has a more complex organizational structure. So we proposed a hybrid representation incorporating both continuous gradients and distinct puzzles. So the multi-scale subcortical atlas. So here is the link for the atlas downloading. We give the name the Melbourne Subcortex Atlas. So please feel free to download and use in your connector mapping and whatever study you are interested. And if you are also, and also here, check out this preprint. If you are also interested to know how subcortical topography relates to the intrinsic organization of the cortical networks and how subcortical functional connectivity explains variations in reward and goal-directed behaviors. Yeah, I don't have time to discuss them further, but if you are interested, please go to this preprint. There are more details there. And finally, I would like to thank everyone being involved in this project, including my supervisor, PhD supervisor, Andrew Delaski, and other collaborators, Michael and Daniel, and all the other friends. And particularly, I would like to thank everyone who has been listening. And I think it's time for questions. Any questions? Thanks.
Thanks for the talk, Ye-Tian, although I guess you recorded a while ago. We have a few minutes, 4 minutes before the next talk is supposed to begin. There are a few questions from the audience which I've collected. There are 5 questions. Let's see how many we can go through. I have a few questions myself, but let's start with Stefan. Stefan was wondering whether you can compute the similarity matrix also for symmetric measures of connectivity, asymmetric measures of connectivity, or only measures that are symmetric, like F's function connectivity.
Yes, so first, thanks for the question. So I think the answer is yes. Yeah, but then I would like to, for me, if I want to compute any, for instance, some connectivity measure with directionality, I would like to maybe just take the upper triangle and compute the similarity, and then take the lower lower triangle to compute the similarity. So we would potentially get some cortical gradients that show different patterns when you look at the asymmetric phenomena. I think so, but I've never tried, but I think will be something interesting to say. Typically we look at cortical gradients will be somehow arranged from here to there, but maybe if you look at asymmetric measures, we can have more insight. That's my understanding.
Cool.
这是电影。
Oh, what was that?
Don't know.
Okay.
I don't know who it was.
Thanks for the answer. I'm not sure if Stefan is satisfied, but I am, so I'm gonna move on. So
thanks.
I'm gonna jump to another question because I was also interested in a question as well. In your talk, you basically just used the first principal gradient, right? Is there a reason why you ignore the like the second or the third principal or the second or third gradients? And whether you think that
Yeah, I have looked at all the gradients in terms of the first three gradients that explain the majority of the variance. But in terms of just when I compute the gradient magnitude to define the local transitions, when I look at the three first gradient 1, 2, 3, I found that, so first of all, the gradient magnitude images are quite similar. I compute the similarity across them. And also the locations of the transitions is very consistent across the three gradient. So even though when you look at eigenmap, the direction of the gradient is different, but the actual gradient magnitude, the big gradient magnitude indicate the functional connectivity transition in the subcortex is quite consistent. So in the end, we only use the first principal gradient to compute the boundary.
I see. Cool. I think we're running a bit short on time, so there's like 3 remaining questions. So I guess for the audience who have questions that are not answered, feel free to contact Ye Tian directly. Let's move on to the next talk. Daniel, over to you.
So if you have any questions, you can go to the preprint. The more detail there. Just advertise a bit. Thanks, everyone.
Thank you.
Fantastic.
Thanks.
And continuing with our advanced cutting edge gradient methods, our next speaker is Kun Hak, who is an associate principal investigator and assistant professor at the Donders Institute for Brain, Cognition, and Behavior. His work focuses on the organization of human visual cortex, cortical plasticity, and health and disease, and novel analytic approaches to understanding fine-grained topographic organization of cortical areas and how this functional organization of brain areas influences behavior. So very excited for your talk, Kun, and take it away.
I'm going to talk a bit about the basic ideas and considerations behind connectopic mapping and spatial statistical modeling. So understanding the fundamental organization of the brain is one of the principal aims of imaging neuroscience. And one popular approach is to parcellate the brain into a mosaic of brain areas with assumed piecewise constant structure and function. This has been extremely useful for understanding how different patches of brain tissue can serve specific functional roles. And it also lies at the foundation of understanding how different functional areas interact with each other. Indeed, by assuming that the brain is composed of a mosaic of brain areas with homogeneous structure and function, one greatly simplifies inference because it enables simple A versus B comparisons, and it also permits outer product models of brain connectivity. Whenever the assumption fails, however, these approaches inevitably lead to inaccurate models of brain organization, and they also conceal local patterns that may be crucial to performing certain neural computations. And the problem is that it's not very difficult to find examples of brain areas that violate the implicit assumption of functional homogeneity, such as, for example, primary visual cortex. Indeed, it is well known that primary visual cortex contains not one, but 2 overlapping modes of variation. One that represents a distance from fixation in visual space, also known as eccentricity, and one that represents the angle around fixation, also known as polar angle. And this retinotopic organization is preserved across the visual hierarchy, which implies that also connectivity is organized in overlapping modes of spatial variation. Now, retinotopic cortex is certainly not the only part of the brain where connectivity is governed by functional heterogeneity and multiplicity. These topographic features can be found across the brain, suggesting that local connection topographies are not just useful for sensory processing, but also for mechanisms of coding, learning, and even reasoning. Now, besides being fundamental to brain organization, functional heterogeneity and multiplicity are also tremendously important for how we can go about analyzing our data. And to illustrate this point, consider, for instance, this brain region, where one mode of organization varies smoothly in one direction. What exact feature is being described by this map is not very important. It can be either stimulus response, task activation, or connectivity. The same principle will apply to each of these. Consider also that this first mode of organization coexists with another mode of organization, varying smoothly in a perpendicular direction. Our measurements, however, would capture the superposition of these two modes. And this means that if we would try to infer the spatial organization of this region directly from the measurements, we would wrongly conclude that things vary along the diagonal. Even worse, if we would attempt to parcellate this region into two subregions, we would end up with two parcels that are clearly nonsensical with regard to the true underlying modes of organization. What we should do instead is a spatial variance decomposition, such that our measurements are decomposed into modes of variation that are biologically meaningful. Now, to achieve such a spatial variance decomposition, we recently proposed the Connectopic mapping framework. It constructs a similarity matrix of all voxel or vertex pairs within a predefined region of interest based on their resting state functional connectivity. This similarity matrix is then submitted to a nonlinear manifold learning algorithm called Laplacian eigenmaps, which decomposes the connectivity fingerprints into multiple overlapping modes of variation called connectopic maps. Now, conceptually, this approach is very similar to the more widely applied variance decomposition method known as principal component analysis, or PCA. However, unlike PCA, nonlinear methods can deal with data that are nonlinearly embedded in a higher dimensional space, such as in this example, where a two-dimensional manifold is embedded in a three-dimensional space. Linear methods like PCA cannot capture the local structure of the manifold and will indicate that the principal modes of variation follow the diameter and width of the Swiss roll. Nonlinear methods, such as Laplacian eigenmaps, on the other hand, try to capture the local structure of the manifold by first representing the data as a graph with connection only between nearby data points. And this graph can then be unfolded by performing a variance decomposition of the graph instead of the data itself. Using this approach, we were able to isolate a mode of variation in motor cortex that resembles its somatotopic organization, as well as multiple overlapping modes in primary visual cortex, resembling that region's eccentricity and polar angle organization. In other words, we were able to validate the proposed framework in regions where we have ground truth. However, one of the more interesting applications of connectopic mapping is to learn something about the functional organization of brain areas where we do not have such ground truth. For instance, to be able to account for functional heterogeneity and multiplicity in brain network modeling, we might want to learn if there are meaningful modes of spatial variation within certain multimodal association areas. In such cases, validation can be achieved by determining whether individual variations in the connectopic maps are related to individual differences in other traits, such as behavior. Therefore, we also proposed an approach for performing statistical inference over the connectopic maps. We borrowed this technique from the geosciences, and in contrast to statistical tests that are common in our field, such as detecting activation or co-activation, it involves a multivariate spatial statistical approach that enables performing inference over the topology of the maps as a whole. To illustrate how this works, let's say that we've successfully extracted one connectopic map. This map may exhibit all kinds of curvature and can be noisy, particularly at the single subject level. But the key idea is that we fit a model to this map by estimating parameters gamma. In our work so far, the model involves a polynomial basis set, but this can in principle be any basis set that is deemed appropriate. And once the model is fitted, the parameters will yield a prediction of the map, which can be compared against the map itself to determine the goodness of fit. Because we use Bayesian regression as a model fitting procedure, we can also compute the likelihood of the model given the data, and thereby determine how many polynomials are necessary to model the map accurately with as few parameters as possible. Now, this approach is not just applicable to modeling spatial maps on a cortical sheet, because it can also be adapted to deal with subcortical structures that are three-dimensional by nature. Finally, because we have just characterized the map in terms of just a few parameters, we can now test whether the topology as captured by the parameters co-varies with behavior. We have now applied the connectopic mapping framework in a number of brain areas and been able to link the spatial organization of these areas to behavior. The general approach in these studies was simple. We applied connectopic mapping to the resting state fMRI data of the Human Connectome project, and then used the spatial statistics approach to obtain for each HCP subject a limited set of connectopic mapping parameters, or CMPs. Next, we leverage the fact that the HCP dataset also contains many behavioral variables for the same subjects, which we link to the CMPs by standard statistical modeling procedures, such as multiple regression and canonical correlation analysis. We and others have now applied this pipeline in a number of brain areas. One example is particularly worth highlighting because it underscores many of the points that were made so far, and it also follows the recommended procedural steps outlined on this slide. The work considered the functional organization of human striatum, and we applied connectopic mapping and spatial statistical modeling to the subcortical nucleus in the basal ganglia. Striatum is a critical component in the brain's motor and reward system, and therefore of great interest in investigations into neurological and also psychiatric conditions such as Parkinson's disease and addiction. And our work was motivated by the observation that existing functional connectivity studies into human striatum often ended up with a subparcellation that did not correspond very well to characterizations of striatal organization in experimental animals. Indeed, the animal studies consistently described the presence of a rostral-caudal gradient relating to both nigrostriatal and corticostriatal connectivity. The human work, on the other hand, described the striatum in terms of subdivisions that appeared to follow a combination of the striatum's anatomical constituents, that is, the caudate nucleus, putamen, and nucleus accumbens, and a discretized version of the connectivity gradient that has been described in the animal literature. In the context of multiple overlapping gradients, this suggested to us that the human functional connectivity studies had failed to account for the functional heterogeneity and multiplicity of the striatum. We thus applied connectopic mapping to the striatum, and the results confirmed our expectation that the striatal connectivity patterns observed in previous work were actually manifestations of multiple superimposed patterns of connectivity. The first pattern showed rather sharp transitions that followed the distinction between the caudate nucleus, putamen, and nucleus accumbens. The second reproduced the rostral-caudal corticostriatal connectivity gradient predicted in the animal literature. And when we employed spatial statistical modeling to summarize this gradient in terms of 9 model parameters, that is a cubic model in 3 spatial dimensions, and submitted these parameters to a canonical correlation analysis, or CCA, we found that individual variations in the rostral-caudal connectivity gradient are related to individual variations in goal-directed behaviors, such as delay discounting. In recent still unpublished work, we additionally found the presence of a third overlapping gradient, which showed a striking resemblance to the spatial patterns revealed by that SPECT imaging, and whose spatial model parameters could be related to dopaminergic mechanisms, such as disease severity in PD, sensitivity to L-DOPA, and the amount of tobacco and alcohol usage in healthy HCP participants. Thus, the striatum is an example of a brain area that exhibits meaningful functional heterogeneity and multiplicity that should be considered before averaging signals from across the striatum or in the context of network modeling studies. In addition, we believe that by decomposing striatal organization into biologically meaningful components, we improved our ability to probing specific aspects of striatal functioning. Now, besides testing whether the estimated gradients express meaningful variance related to behavior, experimental conditions, or group differences, the spatial statistical modeling also enables testing hypotheses about the spatial organization of connectivity within brain areas. And we do this by performing model comparisons. In particular, it enables statistically principled comparisons between different models of spatial organization, such as smooth versus sharp transitions. And this means that it can be used to determine whether the data provide evidence of area boundaries or not. Now, for example, say we're given an estimated gradient in some region of interest encompassing 2 biological areas. If the 2 areas have clearly distinct features, that is, connectivity fingerprints, and if the imaging data is sufficiently precise, the estimated gradient will exhibit a rapid transition at the area boundary, such as, for example, was the case in the first connectopic mapping human striatum. We can now use spatial modeling and alternative hypothesis testing to determine whether the gradient can be taken as evidence of an area boundary by comparing the fits of models of smooth basis functions against models with sharp, that is, stepwise basis functions. Smooth models, such as those based on polynomial or Fourier basis expansions, will require a much greater model complexity. That is, many bases with non-zero weights than models that allow for step functions to model rapid transitions accurately. So to summarize, we argued that the assumption of piecewise constant brain areas is generally violated, and that connectopic mapping and spatial statistical modeling are tools to start characterizing the functional heterogeneity and multiplicity of these brain areas. So where do we go from here? Well, in the first instance, we wish to resolve a number of loose ends. So first is the question of how many higher order gradients are actually meaningful. And this is in part an empirical question that can be answered on a case-by-case basis by assessing a gradient's or a connectopic map's ability to explain behavioral variables. Generally speaking, however, it is a problem of intrinsic dimensionality estimation, which is currently an unsolved problem in the manifold learning literature. A related open problem pertains to the fact that most decompositions lead to orthogonal representations, leading in turn to decreased degrees of freedom for the estimation of higher order gradients, and thereby decreased likelihood that they too are meaningful characterizations of behavior. Second, while connectopic mapping allows for eliciting and modeling the spatial pattern of functional heterogeneity, it does not quantify the amount of heterogeneity. Developing quantitative measures of the amount of functional heterogeneity could be important to determine whether it be reasonable to summarize signals into a single estimate, or to determine if modeling the internal structure of a region is worthwhile at all. It will also be important to integrate connectopic mapping and region parcellation into a single framework. Although the connectopic mapping procedures are relatively robust to small differences in region definition, inaccuracies in definition can affect the results. And the most pronounced differences in results can be expected when one region definition does and another does not include patches of cortex with very different connectivity patterns. If included, most of the variance can be explained by the very different connectivity patterns, yielding gradients or maps with very rapid transitions. And if they're not included, most of the variance can be explained by more subtle and gradual modes of variation. Now, these features can be quantified using spatial statistical modeling, and it is therefore conceivable that region definition and gradient estimation or connectopic mapping are iteratively refined in a single automated estimation procedure. Fourth important direction for future work is to integrate connectopic mapping in brain network estimation. In the face of functional heterogeneity and multiplicity, accurate network modeling requires accounting for the complex hierarchical covariance structure within and between areas. Connectopic mapping and spatial statistical modeling methods provide a means to understanding this structure, but have yet to be incorporated in a framework for network estimation. Finally, it's worth noting that connectopic mapping may lead to new methods for learning in what way the spatial organization of specific brain areas supports specific cognitive functions. For many brain areas, it's still unclear what functions they support, let alone how we should vary an experimental stimulus or task to evoke responses at specific topographical locations. By first employing connectopic mapping, we can derive possible spatial dimensions along which we can expect functional differentiation. And this, in turn, can be exploited to reverse engineer that area's functional properties. Okay, so this is all I have. I would like to thank my collaborators as well as the funders of this work. If you would like to read a bit more about this topic, please check out our latest paper, which will appear in the Gradients of Brain Organization special issue in Mirror Image. Thank you so much.
Wonderful. Thank you. Thank you for an excellent talk. Sorry?
This is really cool work, Koen.
Yeah.
Thank you.
I think, Danny, you're going to say something?
Oh, Thomas, please go ahead.
Yeah, I think there is a couple of questions for you in the chat. Someone is wondering whether, actually, I don't see Koen. Oh, you're there. Okay. Someone's wondering whether how you define the ROIs the method might be sensitive to the choice of the ROIs.
Yeah. That's I'm reading the chat as well, and it says, well, basically I replied to that question in the future direction stuff. There is some sensitivity to the gradient estimation with regards to region definition, obviously, because you're trying to characterize differences in connectivity. Mm-hmm. So if you happen to include just a bit of an area with very different connectivity patterns, that will drive the variance decomposition in a way that you might not expect. So the region definition is definitely important. Now, we did typically do that in areas or we have so far done it in areas where we are pretty sure how we ought to define the areas. But like I said, it's conceivable to think of methods that do an iterative estimation where you start exploiting the gradient mapping to detect boundaries and refine the area definition and re-employ the gradient methods yet again. And at one point that should converge relatively quickly.
I'm curious. Oh, sorry. You were going to say something?
I was just curious along those lines. I mean, there are other embedding approaches that would be less sensitive to outliers. Have you evaluated your approach against those?
We have evaluated it against a few other methods. There are a few classes of nonlinear decomposition methods, and they have different cost functions, if you will. And one of the choices that you need to make is, okay, to what extent do these cost functions apply to the question that I aim to answer here? Now, what we tried to do was say, okay, well, we have a few areas where we have some idea of what the connectivity variation is. So we have some kind of ground truth. And we found out that the Laplacian eigenmaps was the simplest and method that yielded results that corresponded to what we expected to see. Other methods, like, for example, isomap, locally linear embedding, those kind of things, slightly different ones, in some cases yielded similar maps. In some cases were completely thrown off. The biggest difference was the difference between nonlinear versus linear decomposition methods. So that's, again, suggesting that whatever we're trying to decompose is slightly more difficult problem than your general PCA problem. Now, I have not directly compared it against every method, but think of it in this way. Every nonlinear manifold learning method can be mathematically re-expressed as something that we would call a kernel PCA. And the kernel describes your cost function. So you can conceive a study where we have systematic variations in what types of kernels we allow for and how they affect the gradient estimations. But again, it's largely an empirical question that where you wonder, okay, well, is this optimization problem actually trying to give me the answer that I aim for? So for example, if we have isomap, it's a more global method, and for that reason, a bit more sensitive to a lot of noise in the data. Again, what they would call short circuit. And that means that it's probably less applicable to very noisy data, but might be better suited in very high quality data. So there are always costs and benefits to these things.
Fantastic.
Awesome. There are more questions for you, Koen, in the chat. I'm sure you can. I guess you can continue answering them if you wish. For now, you can answer them in the chat. For now, we will move on to the next speaker, who is going to be Reindeer van der Wal. I hope I'm pronouncing the name correctly. Reindeer is a PhD student with Boris, and he wrote the BrainSpace Toolbox. So without further ado, I think let's start the talk. You need to turn on the sound.
How you can create gradients. So this talk, I'm going to tell you about how we use gradients to uncover the organization of the human brain, as well as how you can create gradients from your own data sets to use in your own research. But before I get into any of that, let me first take a moment to talk about why we use gradients in the first place. So, the human brain is a hugely complex structure. And if we want to do whole brain network analyses, we have to simplify it in order to make sense of it. One way in which we can do this is by parcellating the human brain. Now, this already dates back to at least the early 20th century. It was the release of the Brotman atlas. Brotman defined regions of the brain based on cytoarchitecture. And we have continued with this throughout the history of neuroscience. with many neuroanatomists creating their own atlases, and once MRI became big, many neuroimagers creating their own as well. For example, the Euclidean atlas based on functional connectivity of the human brain. However, whenever we parcellate the human brain, we always make an implicit assumption, which is that we assume that there are hard boundaries in the brain, and we assume that the regions that we define are homogeneous. And this is close enough to the truth that we can generally work with it. However, for some types of hypotheses, this poses a problem. Consider for a moment that you had a hypothesis that some marker in the brain changes gradually. Well, parcellation approach fundamentally cannot handle that. Think, for example, of something like the tethering hypothesis. In the tethering hypothesis, it is posited that the sensory regions of the human brain are very closely regulated by molecular cues during development. However, as you move further away from these regions, the molecular cues play a smaller role in the development of these regions, and their development is regulated more by self-regulatory mechanisms. So it implies this gradual change from sensory toward association areas. If we want to get at such hypotheses, we need methods that do so. We need methods that allow for gradual changes. And this is where the gradient techniques come in. What you see here on the right are probably some of the more well-known gradients. They're the functional gradients of the human neocortex, as shown by Daniel Margulies et al. And how you can read this is that colors that are similar to each other have similar connectivity profiles. Colors that are dissimilar to each other have dissimilar connectivity profiles. Now, we don't need to define any a priori boundaries or regions to these gradients. It's completely data-driven. And we can actually start talking about distance here. We can say that within gradient 1, the angular gyrus is closer to the precuneus than it is to the visual cortex. So in that way, it has some desirable properties that we cannot get at with the parcellation approach. So what kind of things can we really do with a method like this? Well, for one, we can decompose the whole brain into its gradients, as I showed you in the last slide, but we don't need to do this at the whole brain level. We could easily do it at a regional level, such as the cerebellum, as Gul et al. Did. In a study with Subcortical-cortical et al., we computed the first gradients of functional connectivity for healthy controls, as well as for patients with autism spectrum disorder. And what you can clearly visually appreciate is that the default mode network in autism spectrum disorder is far closer to the rest of the brain than in healthy controls, indicating that the default mode is less separated from the rest of the brain in autism spectrum disorder. So those are things that we can do with just gradients. However, we can also use gradients to relate connectivity to other markers of the cortex. In a study by Julia Huntenberg et al., they related intracortical myelination to the first gradient of functional connectivity. And what they found is that there's a significant association between these. In a different study by Charlotte Murphy et al., she used the gradient to stratify another marker. In this case, she had the parameter estimates of a 0 back and a 1 back task and stratified them by the principal gradient. And what you can see here is that the 0 back task provides higher parameter estimates at the lower end of the gradient in the sensory regions, but provides lower estimates in the higher portion of the gradient, that is in the more transmodal regions. Now here, we're only really looking at one gradient and comparing it to some other cortical marker. However, we can also look at more holistic analyses that incorporate information from multiple gradients. And this is really where gradient space comes in. So you've already seen an example of gradient space. If you've looked at the logo of this workshop, you'll see that the left half of it is the first gradient, the functional connectivity, and the right half is gradient space. Particularly the y-axis of the scatter plot is gradient 1, and the x-axis is gradient 2. Now, if that isn't entirely clear yet, simply have a look at this figure from Daniel Margulies et al., which is basically showing the same thing here. If the scatter plot with gradient 1 on the y-axis and gradient 2 on the x-axis, the points are color-coded by their position in this space, and those colors are projected to the cortex. And you see this default mode sensory distinction. And now we can use gradient space to analyze other properties of the brain. For example, in the same study by Subcortical-cortical et al., you can see the gradient spaces of healthy controls and of autism spectrum disorder at the top. And again, you can see that the first gradient is somewhat contracted in autism spectrum disorder. But what we can also do is do a stepwise connectivity analysis to look at how a signal propagates through the network, but display that in the gradient space. And what you can see if we do a stepwise connectivity analysis for healthy controls, here in the bottom left, if we start off in any of the sensory regions, be it visual, somatomotor, or auditory, and look at how a stepwise connectivity moves through the gradient space there, we always end up in the default mode area. However, in auto-inspection disorder, this simply doesn't work the same way. If we see from the somatomotor or the auditory cortex, then we start moving up toward the default mode, but then veer off. And if we see it from the visual cortex, then we just sort of get stuck. So that's the kind of things we can do with a gradient analysis. We can look at the gradients by themselves. We can compare the gradients to other markers, or we can use the gradients as a visualization technique to see how other markers travel through this gradient space. So let's now have a look at how exactly we build the gradients. So we start off with some input matrix. In all the examples I've shown you here, this was a functional connectivity matrix, but it need not be. We then compute what we call an affinity matrix. Now the affinity matrix denotes the similarity between each of the seed regions. At its simplest, you could just do a Pearson correlation of every pair of rows. This would give you an affinity matrix. In this example, we use cosine similarity, which is very closely affiliated to the Pearson correlation. Next, we apply some dimensionality reduction step. This could be a principal component analysis. More generally, in the gradient literature, diffusion map embedding is used, which is essentially a nonlinear principal component analysis. Whichever method you use, it'll provide you with a set of eigenvectors, which we also call gradients. And we could plot those, color code each point by their position in the gradient space and project that to the cortex. Now, if this all sounds very complicated to you, you're in luck, because we've tried to make it as simple as possible. We recently released a toolbox called BrainSpace, which is a Python MATLAB toolbox for the computation, visualization, and statistical analysis of gradients. Documentation available, you can see at the bottom left, and a GitHub on the right side. Don't worry, there will be a link to this at the end of the presentation. Now, before I get into BrainSpace, let me first give a quick shout out to a few other gradient packages that are also out there. If you're interested in gradient type analyses, have a look at these. There's the MapAlign package by Sattvar Ghosh, which is specifically for diffusion map embedding. This is what Daniel Margulies used in his paper. There's the Connectopic mapping package by Koen Haak. He's presenting in the same session, so I'm sure he'll tell you more about that. And there's the cerebellum gradients from the same paper I showed you before. So let's take a bit of a dive into the BrainSpace package. Now, in this section, I'm only going to show you the MATLAB code. If you're a Python user, have a look at the documentation. The code is very similar. We've tried to make sure it matches across the MATLAB and Python implementations. So if you want to compute your own gradients, the first thing you do is you instantiate a gradient maps object, as you can see here on the first line. Next, you simply fit your connectivity matrix using this object, and you've now computed your first gradients. But just for visualization, we can extract the first two from this object, as you can see on the third line. And then we plot those gradients on the hemispheres with the plot hemispheres function, which is also provided by the BrainSpace package. And as you can see, the first gradient here describes the default mode to sensory dissociation, and the second one is the sensory dissociation. So that's how we deal with building a simple gradient. However, imagine that you want to build gradients across groups and compare these to each other. One thing you need to be aware of is that during the dimensionality reduction step, the eigenvectors that you find might describe different subspaces. One thing to get around this issue is to align the gradients after we've done the decomposition. Again, in BrainSpace, we've tried to make this very easy. If you want to apply a Procrustes alignment, which is essentially a linear rotation, when you instantiate the gradient maps object, you add the alignment name and add the PA value, which simply means use the Procrustes alignment. Next, during the fitting, we define that we want to fit it to two different matrices instead of just one, and then the alignment will be done for you. So if you look at the plotted unaligned here at the top, you'll see that gradients one of these two groups are exactly opposite of each other. It's something that happens very often. But after alignment, they are in exactly the same space, and we can use this in our follow-up analysis. So the next thing I want to talk about is null models for gradients. Something that you should be wary of when dealing with neuroimaging data, but especially with gradients, is the autocorrelation inherent to neuroimaging data. What that means is if I know the value of one voxel, I have a pretty good estimate of the values of the voxels around it. This means that our measurements aren't independent of each other, and that is an assumption built into many statistical models. One way to get around this is by building surrogate data that has the same spatial autocorrelation, but otherwise isn't correlated to the original data. And then we can compare our gradient both to the marker that we want to compare it to, get a true test statistic, as well as with the surrogate data. And from there, we get, say, 1,000 surrogate test statistics. And then we simply look at what percentile does our true statistic fall. So here's how we do that with BrainSpace. So first we define that we want 1,000 permutations. We want 1,000 random data sets. And then we simply use the spin permutation command. We supply it with the T1 over T2 intensity data that we want to apply the spin permutation to. We supply it with the spheres of these cortical surfaces. This is something that FreeSurfer and Civet provide by default. And we tell it that we want to use 1,000 permutations. And you can see what happens at the bottom. We start with a T1 over T2 intensity, and we project that to the sphere. Next, we rotate the data on this sphere, and then we project it back to the cortex. And what you can see is that that high intensity band in the somatomotor cortex now ended up in the visual parietal areas. Now we do this 1,000 times, and we can make this histogram here of the correlation between gradient 1 and each of these rotated markers. And then the vertical dashed line denotes the true correlation between T1 over T2 intensity and the first gradient. Now, because this falls below the 2.5th percentile, we judge it to be significant. So what I hope to have shown you in this presentation is that gradients provide us with a low-dimensional summary of our high-dimensional data. We can use it to relate connectivity to other markers, such as T1 over T2 intensity, such as stepwise connectivity, and they're very easy and very fun to build with BrainSpace. Of course, no project is built alone, and BrainSpace especially so. While I can't go through the full list of acknowledgements, I'd just like to point out Boris Bernhardt and Wally Benkrum, who both worked tirelessly with me to get this package off the ground. If you have any questions, I should be here in the Zoom chat. You can also tweet at me. My handle is over here. You can email me at the email address you see here. If you want to get started with BrainSpace, I highly recommend you start by going to the documentation. This also has links to the manuscript and to the GitHub, so you can find everything from that link alone. And with that, I'd like to thank you for listening, and I'll be here to take questions.
All right. Wonderful. Thank you for your talk. And, oh, Thomas, go ahead, actually, sorry.
Wait, what? Feel free to, yeah.
Take it away, take it away, sorry.
Okay, sure. There are a few questions from the, from the chat window. Someone asked you if you can talk more about the stepwise connectivity that shows the altered trajectory through gradient space.
Yes, so I was doing answering now, so give me 10 seconds. I was gonna answer this. I'm Seokjun, by the way. Sorry.
Oh, okay, yeah, sorry, I didn't. So Seokjun's the first author on that paper. He did the actual analysis. So if he's writing up an answer on that, then
sure, I'm
not going to compete with his answer.
Great.
Wait, sorry. What did he say? He's going to write. Is he going to answer?
Yes.
Or?
Yeah.
Yes. Apparently he's.
So I was gonna write a type in
the
chat.
He's going to reply. Oh, okay. Sorry.
Yeah.
Okay. Next question is that is there another alignment method besides Procrustes or that is being implemented, or yeah?
Yes. So BrainSpace provides two different alignment methods, which are the only two I can think of off the top of my head which have been used. So Procrustes is one of them. This is essentially just a linear rotation. It's a very simple, runs very quickly. The other is a joint alignment. In a joint alignment, we essentially concatenate the matrices, compute the gradients simultaneously, and then basically deconcatenate them at the end. What this does is generally the alignments are a lot better because the gradients are computed simultaneously. The problem is that they're no longer independent of each other.
Right.
So if independence across your modalities or your subject cohorts or whatever groups you're comparing is important to you, then the joint alignment isn't very workable.
So if you concatenate, it becomes like a huge matrix, is it?
Yeah, exactly. So you have, for example, a functional connectivity matrix and a structural connectivity matrix. You concatenate them across the row dimension.
I see. I
from
see.
the gradient.
Okay. Thank you. The next question is the direction of the gradient arbitrary? Can we flip the direction of the gradient? Yes.
You can always multiply a gradient by -1 if you want to. The reason for this is essentially the gradients are eigenvectors. And if you multiply any eigenvector by a scalar, it is still an eigenvector.
Okay. There is, someone also asked, is it possible to use the spin permutation for volumetric data?
No. So the spin permutation requires that you have some sort of surface sphere. So by definition, it cannot run on volumetric data unless you first project it to a surface.
Mm-hmm.
If you do want to do something like a null model for volumetric data, BrainSpace Toolbox does provide more in spectral randomization as one option, which can work for volumetric data. And there's also other
randomization?
More in spectral randomization.
Mm-hmm.
There are also other tools for this out there for volumetric null models that we haven't implemented.
Mm-hmm. I think John Murray is giving a talk later. I think he might be talking a bit of that about that too. Yeah. Other questions? Or Daniel, do you have questions?
Sure. I guess one of the topics that has come up is interpreting these in the framework of hierarchies. And of course, that is a challenging one that I think we're struggling with. Do you have any thoughts about the justification for thinking about these spectra as hierarchies, or how to further explore that?
So I consider that more of an empirical, consider that more of an interpretation on what the data provides, right? So the gradients themselves, purely as sort of the mathematical underlying technique, don't have any direction to them. There's no top or bottom to them. It's the interpretation that we give because we have this hierarchical view of the brain with the default mode on top and the sensory mode is just the unimodal at the bottom. We often interpret it as a hierarchy, the gradient as a hierarchy. But this is, in my view at least, purely a theoretical view that we have and not something that derives from the technique itself.
Cool.
Okay. Should we? There is one last question, but perhaps apparently there's 5 more minutes after this that we can discuss. So, shall we move on to the next talk from Mac? Daniel, go for it.
Absolutely. Yeah. Thank you again for a wonderful talk, Rainer. Okay, our next speaker is Mac Shine, who is a Robinson Fellow at the University of Sydney, and investigates the factors that drive network level reorganization of the human brain during cognition. So looking forward to your talk, Mac.
Hi, everyone. Thank you so much for having me. It's a real pleasure to be associated with a really exciting workshop just like this. So today I'm going to be talking about some work that have recently been conducting in my lab with 2 really talented postdocs who work with me, Eli Muller and Brennan Munn. And in general, we've been really interested in the idea of trying to understand the kinds of benefits and constraints that the thalamus, a deep diencephalic structure, imposes on the low-dimensional organization of the brain. Particularly the cortex, the cerebral cortex, which we think of a lot as an on-brain. And so people in this audience will be quite familiar with this idea of calculating low-dimensional gradients in cortico-cortical connectivity, let's say the resting state, and that this gives us a way to make contact with these really beautiful ideas. This is a figure from some prophetic work by Marcel Nesselin back in the late 90s, thinking about these low-dimensional structures that are present in the cerebral cortex and how they might relate to our abilities, cognitive and otherwise. And for the fact that the cerebral cortex is so obvious visually and is quite clearly expanded over phylogeny. A lot of our models for whole brain function, things like cognition, are quite corticocentric. This is a picture of a predictive processing model where predictions are passed backwards from agranular to granular regions, and then the difference between the inputs and those predictions is propagated up the hierarchy from granular to agranular regions as prediction error. But I think it's really important that we start to think about the cortex acting in concert with subcortical constraints imposed by regions, in particular, like the thalamus. So in this case here, I'm showing you on the left-hand side a cutaway where the thalamus in green, these diencephalic structures, you can see them sitting. There's one on the left and the right. They're sort of nestled in there with the fimbria, the hippocampus, as well as the caudate and the putamen, the basal ganglia. Right behind them are the pineal body and the superior and inferior colliculi. So that there's really this really crucial core of grey matter structures sitting deep within the brain. And it's been known for a long time that they have different kinds of inputs to the cerebral cortex. We know that a lot of the thalamus receives input from the cerebral cortex, either from layer 6 cells or layer 5 pyramidal cells, and it projects back to them and either hits the granular layers here from a really beautiful projection from the blue brain group, or the supragranular layers. Which is where a lot of the feedback connections from agranular regions are actually received by the cortical inputs. And so traditionally, there are lots of different ways to think about the thalamus. Murray Sherman's popularized the idea of first order, i.e. regions that project, let's say, a sensory signal straight forward into the brain, into the cortex, and higher order, which are regions of the thalamus that, instead of receiving sensory input, receive input from the cortex and then feed back to the cortex. You can think of them as a sort of embedded loop within the central nervous system. The dichotomy that I'm quite fond of, and I'm going to speak a lot more about today, is an idea popularized by Ted Jones, which is the idea of a core matrix architecture. So in this case, the core nuclei are sets of individual cells that are present within pretty much every single larger cellular group or nuclei within the thalamus. And they typically receive inputs from either the sensory apparatus or the spinal cord or the cerebellum, and they project forward into the granular layers of the cortex in a quite targeted way. They're interdigitated within each of these different nuclei in a mixture, are actually a different population, which Ted Jones called the matrix population. And these instead project up to the supragranular regions of the cortex, and they project in a quite diffuse manner that often crosses obvious functional boundaries. Okay, and they're going to project up and hit the supragranular layers and hit different kinds of cells and different regions within those cells in the cortex, and can theoretically push them into a different processing mode. So one of the things that we're really interested in is trying to work out what having a system that has these different levels, these types of organizational principles in it, could buy you at the systems level. Now, fortunately, there's a way in here, which is that these different thalamic populations express different calcium binding proteins. So the matrix cells express calbindin, and to a lesser extent calretinin, and the core cells, at least in non-human primates and humans, express parvalbumin. And so what we can do is we go to the Allen Brain Atlas, which is a repository of 6 individuals that post-mortem had their brains donated to science, and then every single region of their brain was essentially conducted, a genetic test was conducted that looked at the levels of mRNA expression of a range of different genes. And what we can essentially do then is look at thalamic regions of interest, and we can go in and we can ask what the relative expression of calbindin in blue or parvalbumin in green was. And what that lets us do is essentially create an estimate of the likely population level activity within those 2 different classes. And you can see that across the thalamus, there's a sort of general gradient of expression of these two different calcium binding proteins, which we can use. And so when we then correlate the time series with the time series of a set of 400 regions from the cerebral cortex, in this case, it's a 7 Tesla data set, 60 subjects, which we was provided by one of our collaborators, Luca Kochi from Queensland. we're actually able to show that the parvalbumin cells or voxels within the thalamus were much more likely to have strong correlations with visual, temporal, and somatomotor areas, whereas the carbinin population were much more likely to correlate with posterior cingulate, regions of the frontal, medial frontal cortex, as well as the lateral frontal and lateral parietal cortex. And then down the bottom, I'm just showing the relative mean within each of the different 17 subnetworks of the US17 parcellation. And so this little map at the top should actually look quite familiar to people in this audience. Namely, we have a Margulies alert. We found through completely different set methodologies, we can take genetic architecture of the thalamic voxels, and we can then look at their time series, and we can actually recapitulate this primary resting state gradient, which we would normally find by, let's say, getting vertex to vertex connectivity measures and then performing some kind of dimensionality reduction on that data. It's worth mentioning as well here that this result survives correction for spatial autocorrelation, in which we use the spin test to populate a null distribution. And so, so we thought that was really interesting, that we could basically take thalamic architecture and then recapitulate cortical connectivity patterns in a low fashion. Brandon Munn, one of the really talented postdocs in my lab, was really interested in whether or not this pattern of sensory to associative connectivity that was recapitulating the thalamus might also relate to the kinds of timescales that that the system is able to process. And the idea here is that sensory regions are able to sort of refresh really quickly, whereas the regions like associative regions, frontal parietal cortex, are actually able to process information over longer timescales. And so to test this hypothesis, he calculated the Hurst exponent on each cortical parcel, and then related that to the relative connectivity between the matrix thalamus, i.e. the calbinin positive thalamic cells, and the parvalbumin positive, or the core thalamus. And we essentially found a positive correlation that again survived the spin test. Eli Muller, another really talented postdoc in my lab, was really interested in making contact with this notion of the attractor landscape. We find this a really intuitive and rich framework in which to view the idea of state space dynamics. The idea is that you can envisage the particular brain state at a point in time as a ball sitting upon a topography and attractor landscape, where the depth of the well that the ball is currently sitting in tells you something about the stability of the current state, whereas the flatness tells you about the ability for that ball to roll to a new state. And so the idea might be that if you had the core system driving really hard, it might be something like the depth of this well would decrease, so you stay stuck there, right? Whereas if you wanted to get to a new state, what would actually be really beneficial is if you could squirt in a little bit of variability, if you could increase the temperature of the activity patterns that were allowing you to reach that new attractor, and that might be this green ball here, which can then overcome that activity, that energy, and then find its way into this new state. And Eli was essentially able to find evidence for this phenomena. The idea here is that he calculated time varying functional connectivity with a range of different windows. But for each window length, he essentially calculated the variability of the dynamic connectivity pattern across all of the windows for each region. And then we were able to show that the regions that had the most variable dynamic connectivity, are the ones that were able to configure into multiple different zones, multiple different types of configurations, were the ones that were supported by the matrix more than the core thalamus, which again I think fits with the intuition that the matrix thalamus was able to buy you this ability to reach a new brain state that you couldn't have otherwise reached. In the next little part of the talk, as a sort of a way to kind of conclude and wrap up some of these ideas, I wanted to talk to you about some of the computational work that Eli and Brandon have been conducting in the lab that's essentially trying to put some mechanistic basis underneath a lot of these ideas that we've been discussing so far. The idea is what we can do is we can take a really well-established cortico-thalamic neural mass model, which really does look an awful lot like the core thalamic connectivity pattern where you have an excitatory cortical population projecting down to a relay nucleus in the thalamus and then projects back up to the population in the cortex in a kind of little feed-forward loop. And then what Eli was able to do is then put in a variable amount of diffuse connectivity, which would represent something like the matrix thalamic input. And as he turned it up and down, the idea is he could start to work out what was the benefit of the system being organized in that fashion. You could think about this as analogous to heating up a glass of water. And the idea is that as you slowly heat up the glass of water, more and more regions that fall on the right tail of the distribution of temperatures within that glass will actually then be able to think that the temperature is hotter than it actually is. And then they can essentially move into a different kind of a brain state, a different kind of a state in the case of water, but that might be a different brain state in the model that we're conducting. So you can think about this as the system being enslaved to a lower attractor. But if we squirt in enough diffuse coupling, now all of a sudden a small group of regions can kind of break away from that enslavement and do something a little bit different. Let's say fire at a higher rate, or congregate into a small neural assembly that might allow you to process some information in a contextual fashion. So we think that this might be the really key computational benefit of having a system that has this ability to project in a diffuse manner and really sort of raise the temperature of the cortical population without necessarily passing a message between regions. And so this slide is just to demonstrate that you can take this parameter, sweep it through a range, and take the system from one in which there's a very little activity and everything's quite subcritical and damped, to a region of saturation where everything's sort of spiking away, but in a really information poor way. And the transition between these two, which we call the quasi-critical regime, is really crucial because a little bit more diffuse coupling allows you to actually reconfigure the brain state in this model and process information in completely unique ways. One example, there's plenty more in the paper if you're interested, but one example that I think is really telling is that if you take these regions, the different nodes in each of these different regions, and you ping them with a identical input in each case, what you can find is that in the subcritical zone, regions essentially all come back to their baseline at the same rate, whereas in the quasi-critical zone, you actually start to see a separation where the regions that were further to the right in our original model, the closest to that bifurcation, the ones that had sort of realized a higher temperature, were actually able to move into a completely different functional mode. And you can get this really interesting separation of timescales that can allow you to have sort of subtle interactions amongst regions that you couldn't have in the subcritical or the saturated zone. I don't have time to get into it here, but you actually see a lot of the same signatures of complex adaptive dynamics that people have found in different systems level neuroscience experiments. So for example, the network becomes more integrated and more low dimensional as you move into this quasi-critical regime, which I think is really important. And it actually recapitulates some work I did with Luca Cocci and colleagues, where we took a Latin squares task, which is a little bit like Sudoku, and we're able to show that the low dimensional state space dynamics in the cortex are actually quite similar to a lot of the dynamics that were happening in the thalamus. In this case, we were partitioning the thalamus into different nuclear compartments rather than genetic compartments, but I think the same intuition is consistent in these two different approaches. And so essentially what we could do, right, is we could take now data from, in this case, an NBAC task and REST, and we could ask where in that landscape of diffuse, relatively low diffuse to relatively high diffuse coupling does our brain fit. And essentially, Eli had to create his own model fitting algorithm, but you can see that we find evidence that the NBAC task is better explained by a higher level of diffuse coupling and a more quasi-critical brain, whereas the resting state was more consistent with a subcritical or maybe lower side of quasi-critical. So in summary, I really want people, at a high level to be thinking the cortical structures that we see, the cortical organizing principles that we see, ought to have relationships with these really highly conserved subcortical systems, in particular the thalamus, but there's a range of others, the striatum, the hippocampus, the amygdala, the superior colliculus, the hypothalamus, that are really worth thinking about when we start thinking about these sort of higher level systems and how they're coordinated. And with that, I'd like to say thank you. And please, if you're interested, check out the work on BioArchive. A huge thanks to Eli Muller and Brandon Munn, who did a lion's share of the work here. Thank you very much.
Fantastic. Thank you for the talk, Mac. Are there questions? Oh, here we go. So Boris is interested if there's a lot of inter-individual variability in the core matrix population, or is this architecture consistent across individuals?
Yeah, great question, Boris. I think with the limitations of the data that we have with the AHBA, I mean, beggars can't be choosers, but an N of 6 of humans post-mortem is really sort of not at the level where we can start to ask those questions, I think, and get really solid answers. But you know, if I was going to start to speculate as an Australian at 10:45 in the evening with a couple of glasses of wine on board is permitted to do, I would say that I think there should be, there would be a lot of inter-individual variability in these kinds of circuits. And I think that you'll both see genetic differences, but also differences that come out over the course of development and in the course of sort of interacting with the kinds of environments that an individual gets put in. I think if an individual's raised in a really, you know, simple environment where they can sort of trust the input-output, you might see a certain kind of relationship. But then if they get put into an environment where they have to move on the fly and have to do a lot more sort of exploration than exploitation, you might just see more pressure being put on the matrix system to kind of push you into that more variable location to flatten the landscape, as it were. And so I could imagine that becoming reinforced. And that's those systems that kind of come down probably from the frontal cortex to recruit those thalamic systems and use them in a context-sensitive manner would become really crucial for those kinds of flexible cognitive behaviors that we think of, you know, this sort of explore dynamics.
Great, thanks.
And sort of along those lines, extending that, Sophie is interested in how those states relate to behavioral states themselves.
Yes, so great question. And we could use all the help we could get trying to work out how to even ask those questions appropriately. One of the major focuses of the lab at the moment is trying to work out how to appropriately contextualize sort of brain state dynamics in cognitive tasks. A major challenge that goes back to a book that Daniel recommended to me a couple of HBMs ago by Michael Spivey, which is called The Continuity of Mind, which basically argues, amongst other things, that one of the big challenges faced by cognitive neuroscience is that we don't have continuous measures of performance in tasks. What we essentially do is we say, sit in front of this screen, do X, and we're going to measure your answer, and we're going to see if that's correct or incorrect, and we're going to measure your reaction time and see if you did it quickly or not. And we can do things like, you know, forced choice tests, so we can get really good, you know, measures of drift diffusion parameters and things like that. But what we're quite bad at is tracking whether or not right now you're engaging, or right now you had a divided attention, and you had divided attention for a time before you pulled it back and finally got the answer correct. And so until we can get really, really good measures of those kind of dynamic changes over time, and they are out there, don't get me wrong, there's really great work by Dan Wolpert with, you know, moving mice, you know, moving force directed plates. We can track things like eye movements. There are measures out there, but until we get really great ways to map the dynamics of behavior, I think it's gonna be really hard to get really strong correspondence to dynamic trajectories of brain states as they change in really, you know, precise contexts. So anyway, that's all to say that it's a really, really hard problem. And it's a really interesting problem to work on and to think about deeply, and to work out how we can devise tests that are really good ways into utilizing these really exciting, interesting signatures of brain state dynamics we can get out of these approaches that everyone's sort of doing in this field. So I think it's a real big challenge for us to work out how do we do this going forward.
Yeah, awesome work. Thank you so much.
Well, thank you.
Fantastic. I guess one last.
If anyone's curious about the Dan Margolis picture, I had to find it on a slide from HBM a couple of years ago, and extract it and remove the background and then make it spin. But yeah, that was all self-created.
Thank you for that. Speaking of patterns, do you see any other patterns in the principal gradient within the thalamus? Is a question from JS1731.
Yeah, great question. So we plotted the scatter plots of the core matrix gradient versus the top 5 gradients, the sort of principal gradients from Dan and Johnny's paper that was on Neurovolt, hashtag Neurovolt. Everyone that doesn't use it should. It's really awesome. Unthresholded maps of the future. But so basically we downloaded those maps, we extracted the Schaefer parcellation values within each of them, and we have scatter plots. You essentially see the really strong linear relationship between the core matrix gradient and PC and the first gradient, and then a bunch of really interesting but distinctly non-linear relationships in the next 4 gradients. Some of them look a little bit like the little map that we often think of with the gradient 1 and then gradient 2 splitting into 2. We haven't explored that question in great detail, but there's certainly signal in there, I think. But as to how to best interpret that and how to think about that, we haven't spent a lot of time in that space. But if people are interested, you know, there's a question out there to be asked.
Excellent. Well, given the time, as one gradient said to the other, this is going really smoothly. Thomas, I think we should open it up to general questions in our last 5 minutes of the session.
Sure, sounds good.
Great. So thank you again, Mac. And would all the speakers...
Thanks for having me.
Yeah, fantastic. Maybe all the speakers from the session, go ahead and flip on the video. And if there are general questions, feel free to post in the chat. If there are questions between the speakers, feel free to jump right in. Yeah.
Oh, Kun is back.
Yeah. Oh, beautiful.
Sorry, I'm back. Yes, my earpods don't work and my laptop broke down, so I'm on my phone right now, but I'm here.
Great. Are there any general questions? Seems like one of the methodological issues is the reconciling the division between local and global gradients, one could say, as a way to investigate cortical subcortical interaction, for instance. And that seems to be a theme that's run across the talks today. Does anyone have thoughts about how to bring those together in terms of looking at these kinds of connectivity topographies across different structures and their relation to behavior, individual differences? Open question. Okay, we can drill down to JS1731. Who is that actually? Anyone? Okay. How to reconcile the use of functional data, which is state dependent, to reveal underlying structure. Anybody? Feel free.
So, based on the question, you should be able to guess this idea, apparently. Anyway,
That's gonna be on Casey's quiz.
I think one of the ways that you can reconcile that is that while functional connectivity is state dependent, it has many underlying structures that are present across many, if not all, states. So we can still use those to get to underlying structure without being confounded by which state the subject is on.
I do see some variation in terms of the functional states of the brain and how the spatial gradients look like. So they do same, so we say very consistent spatial gradient across different sessions of the resting state, and we also say different spatial patterns in different tasks. And in terms of the structure, yeah, I think I see one thing. Actually, I saw some papers on the insular cortex, and the functional gradient is very consistent with the structural gradient in terms of the myelin architecture and the structure connectivity. Yeah, I think should be something there. So somehow convergent, this function and structure spatial gradient. But yeah, and in terms of functionally, I think it's more some variation across them. We need to somehow categorize. I don't know whether I answered the right question.
So it was actually me, surprisingly, who asked the question. So I think the point I wanted to make is just that when you look at the increasingly complex gradient patterns that we see in the cortex, then what seems to be the case is they are overlapping. And a lot of data suggests that they're actually, they look a bit like modes the brain can be in. So I guess one of the deep questions, if we're going to use connectivity to make inferences about structure, it's really close to what Max Schein was saying, because basically the modes are probably temporally varying, and they must be related to architecture in the sense that the brain is clearly structured to constrain its function. It's just that there must be a kind of mediating factor, like a state, that allows the brain to shift between these two different things. And when we look at the maps, for example, that Casey and other people have done in structure, making the mapping them onto like Daniel's gradient just is quite difficult. I mean, actually, it's interesting that Max Schein shows that it's there in the thalamus, because I think we've seen it in the hippocampus and the insula too, right? And so one of my deep uncertainties about this is how to kind of like resolve the problem, which is that somehow our observations must be highly influenced by modes, but the majority of the use of gradients is to drive its structure, right? And obviously these are very deeply related problems. But I mean, it's just something that I've been wondering about for a while, and I don't know if anybody else has been paranoid about this or has any deep answers to it. But that's that's what motivated my question, really.
I think it's perfectly normal to be paranoid, Johnny, that we're asking questions at the voxel level with millions of neurons, and we're not even quite sure which neurons we're measuring. Some pooled activity of millions of some pyramidal neurons, maybe it's inhibitory neurons, who knows? And yet the brain is composed bricks and mortar of neurons and glia that, you know, inefficiently communicate with each other by, you know, throwing out a bit of chemical whenever they get perturbed by electrical signal. I think the scale-free nature of the brain is absolutely terrifying in some sense when you really stop and think about it for a little while. But I think one of the things that I'm quite excited by is that these kinds of questions, these kinds of vantage points, let's say, of looking at the brain in this kind of low-dimensional gradient fashion, do appear to have some kind of link between the scales. It's not perfect. It's not going to be one-to-one. You know, if we know anything about these sort of complex hierarchical systems with multiple different, you know, scales, none of which is particularly privileged, we think, for interrogating its function, or at least clearly, obviously privileged, is that, you know, there are links there, and it's up to us, I think, or at least some of the scientists in this room, to be thinking, how do we ask the questions that utilize the vantage point we have, the observational model we have at that level, let's say the voxel level, while also respecting the kinds of structure that are present in the microscopic level. They clearly do relate to each other because we have a brain, right? And we're sitting here talking, and we can measure function that relates to, we can measure signatures that relate to function, and it's comprised of the bricks and mortar. So they're related together. The question I'm sort of really puzzling over now is whether those relationships will be linear or really complex and nonlinear. It's probably the latter, which would really suck. But I think there's at least some, you know, early signs that things are mapping up nicely.
I mean, just to push you on that, it feels a little bit like that. I mean, how would you deal with overlapping gradients at the cortex level then? I mean, the particular one that motivated my question is gradient 3 in Daniel's parcellation, because what it just does is it separates the transmodal regions in gradient 1. And that just in my head becomes complicated, because then you're trying to imagine a world where the cleanest mapping to structure to function is to gradient 1, definitely, because you found it. You know, a lot of Boris's work, like Reindeer's work, shows it, and Casey's done some great work, shows the same thing. But the most complicated problem is, you know, like when it's mapping, when all the regions map that structure, how do you recover the ability to separate the default mode from the frontoparietal, which is kind of like one of its features, in addition to being closer to it, like Daniel found, I guess. I mean, my sense is that the smaller regions could be very important for that shifting mode pattern. I guess that's what your working Thalamus suggests.
Yeah, I think that's I mean, there's a lot in the comment you made. One thing I will say is that embracing, if you have like a statistical physicist that sits down the corridor, and this goes out to every one of the 106 participants of this session, go and offer to buy them coffee and then have them like write down a glossary of what they talk about. I've learned so much by talking to people with a physics background, because these kinds of like gnarly, complex, high dimensional problems, thinking about what the 17th dimension looks like and how it relates to the structure of the system, are the kinds of things that they get trained on. And there are weird things that happen there that are very non-intuitive. You know, for example, with the third gradient, right, that splits one of the lower gradients, it's reminiscent of the idea of eigenmodes. Peter Robinson, who's at the University of Sydney, has really kind of driven a lot of the great work in this area. But the idea is that, you know, systems have inherent degrees of freedom, and they can be described by these sort of wave structures, and they interact with one another in some ways and cancel each other out in other ways. And one of the things they can do is they can split lower order modes into higher sort of more high dimensional shapes. I don't pretend to understand it anywhere beyond that level. It's super complicated, but there's a language and a philosophy and a way of thinking about a system where that description is not surprising. It's not surprising at all that gradient 3 sits there. Of course it should be sitting there because it splits gradient 1 in some characteristic way. And so I think, again, another really, really interesting thing to do when you're buying the statistical physicist a cup of coffee is try to learn what they mean when they talk about modes of systems and eigenmodes and what things are surprising and not. I've learned a ton just by speaking with people with that background and trying to understand how could biology utilize these kinds of degrees of freedom in a complex, multi-scale hierarchical system. I'm not pretending to have answers there, but that's certainly a kind of I think a space that we could kind of seek out answers, the integration between physics and neuroscience. And then to your other question, I think subcortical structures are extremely important for constraining specific patterns we see. They're much lower dimensional than the cortex. They are much more conserved across phylogeny. The tectum in a zebrafish looks very similar to the superior colliculus in a human. So, you know, the thalamus is very constrained. There are differences, no doubt, but the basic vowel plan is present. And so if you're seeing really consistent patterns in the cerebral cortex, one place to look is the subcortical structures that are sending their projections up in a very characteristic way and constraining the modes that system can work in. I think it's a really good place to look at as a first port of call.
Awesome.
Okay, so Daniel?
You know, I was just gonna, like, speaking of buying your favorite physicist friend a cup of coffee. Take it away, Thomas.
Yeah.
I think we are basically at the end of our session. Let's thank all the speakers again. I guess for those of us who are, yes, yeah. I think Casey, you're gonna take over, right?
Yeah.
Yeah.
Yeah. Thanks, everyone. Yeah, beautiful start today. So we're going to start back up at about 1:15. That's in about 10 minutes. But if anyone wants to hang around, we're going to play a little gradients quiz, right? So let me just share my screen and we can get started. What you can do is go to www.menti.com. I'll put up the link in a second and you can play along. Okay. So you see there at the top of the screen, you can go to. Can everyone, Thomas, can you see that? You have your microphone on. Everyone can see that screen?
Yes. You mean
Menti?
Yeah, you can see like this empty white screen. It says, who first published on gradients of portable organization? This is going to be our first question. Give you all a second to put in the code, and then you can play along. Oh, We have first answer, one of my favorites too. So as you put it in, as you start typing your answers, we'll see which ones are most important to the speakers here, and everyone playing along. Daniel, yeah. There might be, I think there's like a real answer here as well. I don't know if it's come up yet. A. Nice. Okay. God. Oh, good. Yeah, I think the only disappointing thing to me is that I think Abby is the right answer, but it's spelled incorrectly there. It's with an IE. Okay. So for those of you who haven't heard of the Abby paper that I'm talking about, it was like the first paper on the dual origin. There we go, Abby 19. Oh, sorry, it wasn't Abby, it was Dart. You guys confused me. Abby was doing it on monotremes and Dart showed it in reptiles back in the 20s. Did anyone say Dart? No. Meslin's still very big though, and Daniel's getting bigger by the second. Okay, let's move on to the next question. So what is the most fundamental cortical gradient in your opinion? I have my answer in mind, so I'm excited to see if that comes up. I want to know who put SNR when I could just imagine the limbic being all off the place with SNR. Any other ideas? Magul is number 3. Centrifugal! Yay, that's my favorite. For Quizzle 1, thanks whoever from Nika said that. So SNR, I get it, but you know, you're in a very fMRI world if you're saying SNR there. Distance, I can see, that has to be Sophie. Okay, so I think the most legitimate to me there is centrifugal. Distance still see with fissure. Distance is a very popular one as well, and we see it in everything. So it's going to be cool to see more talks about spatial autocorrelation later as well. Okay, let's move on to another question. This one's going to be a little quiz. So anyone who's logged on at the moment, you're a player. So let's start, and you'll have like just a couple minutes to answer. So is gradients your favorite term? And if not, what else? I've just put a few answers down here so you can choose which one's your favorite. We're looking at between gradients, axes, eigenvectors, dimensions, connectopies, or hierarchies. We see so many different words thrown up in this field, and I know that gradients isn't everyone's favorite. So I want to see what other ideas you all have. Are there any other ones? You can also write in the chat if I've like missed out on the one that you like the most. Oh, sorry, can you see that? There we go. And sorry if my internet's a little bit laggy, but you know, it's also not so important. Okay, let's see what your answers are. Can we? Oh, there we go. Oh, most popular. Sorry, I put a crossover hierarchies because I think that's the most contentious one, but I think every fine. Seems eigenvectors are good to see. That's nice to know. Okay. Next question. Okay. So what's the optimal number of gradients to describe the cortex? We started talking about this a little bit. Mac was telling us all to have a coffee with a statistical physicist. So what do we think? Is it just the Magula is number 1? That's it? Just centrifugal or infinite? I think I've put like a few different options in there. Hopefully everyone's had about time to click their answer. Let's see. Click back and forth. No. No answer. See. Oh, this one was a write-in one. Okay, wow, 9,000. So what do we have? A few 42, good, great answer. Oh, show me a scree plot. I think that's my favorite. Very objective, very, very data driven. Okay, we just have one more question. Let's see what it is. So this one has a real answer. Richard and I went through and counted. What percentage of talks today include a gradient figure from the PNAS paper? We've seen 4 talks so far. So you might be able to guess. There's 12 talks in total. Okay. Enter your bets, do some little quick arithmetic. Okay, let's see. Oh no, I think my internet is dying at the same time. I think we just not, unfortunately. I don't have any. But I was also going to add a bonus because I know Boris also put it in his welcoming notes as well. Seems incredibly popular. Okay, 3, 2, 1. Most people thought 100%. Yeah, it was 75%. For those 3 people who didn't put the figure in their talk, like you're the outliers. So yeah, it's a pretty popular paper, surprisingly, when it's at a gradient symposium. You know. Okay, thanks for playing. That's our first ever gradients trivia I think that's ever happened in the world, possibly the last. Maybe we'll do another one next year. But with that, we just have a couple minutes until the next session, and that's going to be chaired by Johnny Smallwood and Beth Jeffries. So they're going to be running this session, which will be more on the cognitive side of things, about behavior, as well as neurology and hierarchies as well. So I will pass it over to Johnny and Beth. Take it away whenever you like.
Okay, by cognitive, do you mean confused?
Yeah.
Awesome. Okay. Well, is Beth here yet?
Yeah, here I am. Hello.
Okay, awesome.
Boris, thank you so much for all your work organising this fantastic lesson. I'm really enjoying it so far.
Thank you all for helping and for co-organizing.
You didn't do very much, Boris, I don't think. I mean, I got lots of emails. I marked them as unread because I felt like somebody else was in charge. Okay, I've got the schedule somewhere. Okay, so according to my watch, Shoei should be starting quite soon. Shoei here? No? Okay. Oh. How Ting knows where Shoei is, apparently, so that's good. Somebody does. Okay, so I think today we've got like several really interesting talks. As Casey described, these talks are really to do with trying to capitalize on our understanding, our growing understanding of gradients and how they relate to the function of the brain, which is basically to do things. And accordingly, the talks will all focus on different parts of that. I think the first talk is by Shoei, who is a PhD student in supervised by Beth and me. She's going to talk about a really cool study that she has done as part of her PhD that looks at how the principal gradient pattern that Daniel identified in his PNAS paper has some relationship to patterns of cognition as people do tasks. So I guess somebody should push play. No? Okay, there we go.
A gradient from long-term memory to novel cognition transitions through default mode and multiple demand network. Human cognition flexibly guides decision-making in familiar and novel situations. Traditionally, these different aspects of cognition have been ascribed to different neural systems. When the knowledge required by a task is readily available within long-term memory, gradients of default mode are assumed to play a role. In the absence of long-term knowledge, decisions are supported by the multiple demand network. However, human cognition is a continuum, not a dichotomy. Most scenarios locate different positions on this continuum. Contemporary accounts of cortical organization suggested intrinsic connectivity and functional organization may change gradually and systematically along the cortical surface. And the following is what they did. They constructed the whole brain functional connectivity matrix. Take the connectivity graph here. The positions of nodes reflect the similarity of connectivity patterns. If the functional connectivity of two nodes are similar, they would be close to each other. Then they applied a dimension reduction technique to capture the maximum variance along several dimensions in this connectivity matrix. They projected these components of connectivity, these dimensions of variance in connectivity patterns. This figure shows two gradients they have found. Gradients would occupy similar positions along the gradient if they resemble each other with respect to the connectivity component of interest. The principal gradient, gradient 1, extends between the sensory motor regions and transmodal regions. Our study mainly focuses on the first gradient. The principal gradient also captures the spatial layout of yield 7 networks. Principal gradient values for yield networks show orderly transition, and the gradual transition appears in multiple regions. The principal connectivity gradient offers a view of neural organization in which the relationships between systems are graded rather than dichotomous, with transitions between the networks in multiple cortical zones following the same orderly sequence. Motivated by this view, our study explored this general research question: does this cortical connectivity gradient reflect how decisions change in a graded fashion as support from long-term knowledge changes? We would like to answer these specific questions. If we manipulate long-term semantic similarity parametrically, does the functional recruitment change gradually? Is there a spatial correspondence between the effect of long-term semantic similarity and the principal connectivity gradient? Does the correspondence between the task gradient and connectivity gradient appear in multiple zones? Can we explain the spatial layout of semantic networks in terms of their positions along the task gradient? We created an experimental paradigm in which participants decided whether concepts shared a specific feature, such as color. We manipulate their overall semantic similarity parametrically, creating a spectrum of global similarity. For some trials, nearly all features are shared, such as strawberry and cherry. For some trials, only the task-relevant feature was shared, such as color, tomato, and lipstick. We have two conditions. In one condition, probe and target share similar target-relevant feature. In another condition, probe and target don't share target-relevant feature. We examined the parametric effect of global similarity by including it as a parametric regressor. We refer to the parametric effect of this task manipulation as a task gradient. For matching trials, global similarity rating is higher, the accuracy is higher, and response is faster. For non-matching trials, global similarity rating is higher, the accuracy is lower, and response is slower. Global semantic similarity had different impacts on behavioral performance. Consequently, we can compare them to establish whether the functional change along the task gradient reflects the global semantic overlap between probe and target words, or the difficulty of the semantic decision. Semantic similarity would produce parallel task gradient, while difficulty would produce opposite task gradient. We modeled the parametric effect of global feature similarity. This figure shows the estimated effect of the parametric manipulation of global feature overlap. Default mode regions show positive effect of this variable, that is, a stronger bold response when items share more features. Multiple demand regions show negative effect of this variable, that is, a stronger bold response when items share less features. To establish whether there's any correspondence between connectivity gradient and our task gradient, we calculate the correlation of these two maps and found a significant positive correlation across the whole brain. Since we used a semantic task, we wondered whether the correlation would be stronger if we only included regions that are involved in semantic cognition. We defined a semantic mask. We found the correlation is stronger when we only included regions that are involved in semantic cognition. This suggests the relationship between the task gradient and connectivity gradient is to some extent specific to brain regions relevant to semantic cognition. To establish whether functional change along the task gradient reflects the global semantic overlap between the probe and target words, or alternatively, the difficulty of the semantic decision, we repeated the same analysis for non-matching trials, and we found a similar pattern rather than an opposite pattern, suggesting the effects reflect global semantic overlap. We have answered two questions. If we manipulate long-term semantic similarity parametrically, the functional recruitment changes gradually, and there is a spatial correspondence between the effect of long-term semantic similarity and the principal connectivity gradient. And this effect cannot be explained by task difficulty, as matching and non-matching trials show similar pattern. And then we wondered whether the correspondence between the task gradient and connectivity gradient appear in multiple regions. We anatomically defined 4 regions: left lateral frontal, left medial frontal, left lateral temporal, and left lateral parietal. We found a significant correlation between the task gradient and connectivity gradient in all these regions. And then to establish if the response to the task gradient systematically changed along the connectivity gradient within the semantic mask, we assigned voxels into 20 bins according to their values on the connectivity gradient. Some bins located towards regions, transmodal regions, or some bins located toward the unimodal regions. We extracted the parameter estimate values of each bin corresponding to the effect of global semantic similarity. We examined whether the task response showed a linear change across these bins, and we found a linear change along the connectivity gradient in the effect of global feature similarity. This indicates the task gradient changed systematically along the connectivity gradient. Transmodal regions show positive parameter estimate. Unimodal regions show negatively parameter estimate. To examine whether the non-matching trials showed a similar pattern on opposite pattern, we repeated the same analysis and found similar patterns. And then we wondered whether we can explain the spatial layout of semantic networks in terms of their positions along the task gradient. We compared the location of semantic control regions with default mode and multiple demand regions, as defined by the localizer tasks. We used the contrast of easy versus hard of spatial working memory task to define default mode. The contrast of hard versus easy of spatial working memory task to define multiple demand. The contrast of hard versus easy of semantic task to define semantic control regions. We observed semantic control regions, green color, is in the middle of default mode and multiple demand. It's partly in lateral temporal cortex. Here's the summary. The brain's response to the task gradient varied systematically along the connectivity gradient, with the strongest response in default mode when the probe and target items were highly overlapping conceptually. This graded functional change was seen in multiple brain regions. These effects cannot be readily explained by task difficulty. The gradient captures the spatial layout of networks involved in semantic cognition, providing an organizational principle for controlled semantic cognition across the cortex. Here's the conclusion. Cognition is organized in the brain in a graded fashion. The dichotomy between default mode and multiple demand might represent two ends of a gradient. Semantic tasks recruit both networks and the territory in between, depending on the match between input and long-term memory. I'm very grateful to my supervisors and my collaborators.
Okay, thanks for that talk, Shui. I've got some questions in the chat window. One question is, how do you define the gradient bins?
I define the bins based on the principal connectivity gradient value. If the value is higher, it's divided into the top gradient. It is very low, it will be divided into the bottom gradient.
Okay, so you use Daniel's map.
Yes, I think the result I reported here used the Daniel's gradient, but we also computed the gradient for each participant when we explored whether the task gradient and the connectivity gradient can explain the location of the networks.
Awesome. Okay, and so another question is, was the gradient map for individual regions recomputed separately, or was just masked out the entire cortical gradient?
Yeah, I think I just answered that. So I think the results reported here use the Daniel's gradient.
No, I think what they're asking here is when you looked only in a single region,
yeah.
Like for example, the left angular gyrus, was that basically just the bit of Daniel's map, or did you run the gradient analysis simply on that region?
I think I used the Daniel, yeah, for each region, I just plot the gradient value from the Daniel's map.
Okay, great, awesome. And I think that's all the questions from the chat. Does anybody else have questions?
One more question, right? Which region had the highest correlation from Alex?
Sorry?
Which of the regions you analysed have the highest correlation?
I think it's lateral temporal.
I can't see that question.
It's snuck in at the top.
Yeah, I think it's lateral temporal and the lateral parietal.
Okay, so I can't see it. Anyway. Okay, so how are we on with time?
We've got 3 more minutes.
3 more minutes. It's a bit awkward because I can't really, Beth can't really ask questions to Shoei because that would be like repeating her defense. So nobody else. I mean, we can move on to the next talk and then maybe have a longer question and answer afterwards. Or
yeah, for sure.
Okay.
Hello, everyone, and thank you for inviting me to this virtual workshop. In today's talk, I will compare gradients and parcellation approaches for functional connectivity behavior prediction. The brain is active even at rest. This video from Daniel shows the functional MRI signal when the subject is lying at rest in the scanner. As you can see, these large spontaneous activity fluctuations appear throughout the brain. These spontaneous fluctuations during resting state functional MRI can be used to interrogate brain network organization. For example, if we choose a seed in PCC and correlate its time course across the cortex, we can get this famous default network. This procedure is called functional connectivity. If we move the seed region around the brain, we see that the correlation pattern changes a lot, suggesting that adjacent brain regions can have very different connectivity patterns. So this has motivated many studies to extract discrete or continuous representations of brain using functional connectivity. Here I'm showing you examples of gradients and parcellations. Gradient techniques look for continuous representations of brain. Parcellation approaches can be further categorized as soft parcellations and hard parcellations. For soft parcellation, each vertex can be assigned into multiple RIs, while for hard parcellation, each vertex can only be assigned to one single RI. In these three examples, we can see they all capture similar default network structure. Many papers have demonstrated that individual differences in resting state functional connectivity can be used for behavior prediction. Therefore, behavior prediction can be used to assess quality of different brain representations. So in this talk, we focus on behavior prediction and compare the performance of gradient techniques versus parcellation approaches. We consider two gradient techniques, two soft parcellation approaches, and two hard parcellation approaches. I will first introduce two gradient techniques. We first consider local gradient approach pioneered by Steve Peterson's group. The local gradient approach detects the local changes in functional connectivity patterns. This figure is an example of the gradient map. Bright color indicates rapid change in functional connectivity at that location. Dark color indicates slow change in functional connectivity at that location. We also consider the principal gradients developed by Daniel Margulies, where he applies nonlinear diffusion embedding to decompose functional connectivity into multiple principal gradients. We align gradients across subjects and pick the top 5 gradients that will match very well across subjects. For soft parcellation approaches, we include spatial ICA. I guess we all know what is spatial ICA. Basically, spatial ICA decomposes resting state functional MRI data into a set of spatially independent maps and their corresponding time courses. We try different number of ICA components, 50, 100, 200, and 300. This figure shows 10 ICA spatial maps as examples. Another soft parcellation approaches we include is Perfumo. This is a relatively new approach, also from the FSL group. Perfumo explicitly models between subject variability to estimate spatial maps. The red figure shows 10 Perfumo spatial maps as examples. For hard parcellation approaches, we include the Schaefer 400 region group level parcellation shown here. The Schaefer group level parcellation is generated based on a gradient weighted Markov random field model, which integrates both local gradients and global similarity approaches. We also include my 400 region individual specific parcellation shown on the right. We extended our previous multi-session hierarchical Bayesian model for estimating brain networks to estimate finer area level parcellations. So far, I have briefly introduced gradient and parcellation approaches we considered for the comparison. As I mentioned in previous slides, that we focus on comparison between gradients and parcellations for functional connectivity behavior prediction. I will then describe our behavior prediction model. We consider 58 behavior measures from the Human Connectome project. We use kernel regression to predict behavior. Roughly speaking, what this does is that behavior of test subject is estimated to be the weighted average of all training subject behaviors. So a training subject is weighted more if the training subject's gradients or parcellation features are more similar to the test subject. So this similarity is defined based on correlation of gradients or parcellation features between subjects. In this way, we will construct the inter-subject similarity matrix for different approaches. So let's first look at gradient techniques. For the local gradient approach, the inter-subject similarity matrix is simply defined as correlation between subject gradient maps. For example, the highlighted entry is the correlation between gradient maps of subject 2 and subject 3. Similarly, the inter-subject similarity matrix of principal gradients is defined as the correlation between subjects' principal gradients. As we consider 5 principal gradients, we end up with 5 inter-subject similarity matrices. We will use multi-kernel regression for behavior prediction if there are multiple inter-subject similarity matrices. Next, we will talk about inter-subject similarity matrix for soft parcellations. For spatial ICA, assume there are k ICA components. For each subject, we can obtain a k by k partial correlation function connectivity matrix. To construct the inter-subject similarity matrix, we took the lower triangular part of the function connectivity matrix and correlate between each pair of subjects. Similarly, we can obtain an inter-subject similarity matrix for profumo using partial correlation function connectivity. However, in the profumo framework, the inter-subject variability was most captured by spatial maps instead of function connectivity, as shown in Janice and Sam's paper. Therefore, we correlate spatial maps for each pair of subjects and end up with 50 inter-subject similarity matrices. We then average them to obtain a single similarity matrix. In this way, we have 2 similarity matrices for profumo. We then use multi-kernel regression for behavior prediction. Let's move to hard parcellations. For both Schaefer 400 region group level parcellation and mine 400 region individual specific parcellations, we first generate partial correlation functional connectivity for each subject. We then correlate the lower triangular part of functional connectivity between each pair of subjects to obtain the single inter-subject similarity matrix. In the last part of my talk, I will show you the behavior prediction results of gradients and parcellation approaches. Here is the behavior prediction accuracies average across all approaches for 58 behavior measures. The box plot was colored based on how many approaches can predict this behavior very well. So white box indicates all approaches predict poorly for this behavior, and that red box indicates all approaches predict very well for this behavior. The behavior measures are categorized into task performance measures and self-reported measures. We can see there are more orange dots on the left. So if we average across self-reported measures and task performance measures, we can see that task performance measures can be predicted much better than self-reported measures. If we average prediction accuracies across self-reported measures, the pink results are showing prediction accuracies of gradient techniques. The blue results are showing prediction accuracies of spatial ICA with different resolutions and profumo. The yellow results are showing hard parcellations. We can see that overall prediction accuracies of gradient techniques are lower than the parcellation approaches. and the individual specific hard parcellation performs the best. We then average prediction accuracies across task performance measures. Again, we first see prediction accuracies of gradient techniques and prediction results of soft parcellations and the results of hard parcellations. Again, prediction accuracies of gradient techniques are lower than parcellation approaches. To summarize, in this talk, I've shown that individual specific gradients can also be used for behavior prediction. In the kernel-ridge regression framework, overall functional connectivity from brain parcellations outperformed gradients for behavior prediction. We have repeated this with linear ridge regression, and the conclusions are similar. However, we caution that gradient techniques are relatively new, so future research might get further improvements. It is also worth noting that the individual-specific hard parcellation approach actually incorporated gradients in deriving individual-specific parcellations. Further testing in new datasets and other supervised learners would also be desirable. All our software are available on GitHub. This includes the Schaefer group-level parcellation and our kernel-ridge regression model for behavior prediction. The code of the individual-specific hard parcellations will also be released here once the paper is published. I would like to thank our group members and collaborators and our funding support. Thank you.
Great, thanks Ruby for that really excellent talk. Okay, cool. We've got quite a few questions, so I'm just going to start going through them. Okay, so the first one is from Yi Tan, I think, and it says, would the kernel regression be very sensitive to the number of subjects including in the training sample? Did you estimate the proper number of subjects?
Yes, that's true. So, in our analysis, we use a 20-fold cross-validation, and we repeat the entire procedure like 100 times to get a rather robust results. And of course, like if you have very small number of subjects, the prediction results gonna be like pretty shitty for all the approaches. But in our case, we use relatively large data sets, include like a 750 subjects, I think. So basically, I think our results are like not that sensitive, as we also like, as I said, we compute like around 100 times for the 20-fold cross-validation.
Okay, great. There's a question from Eduardo Garza. He asks, how were similarity matrices quantified? Oh no, he's just said never mind. So must have that. Okay. So the next question is from Andrew Zaleski. He says, is variation in feature dimensionality between gradients and parcellations are confound in the comparison? For example, inter-subject correlation matrices may be resolved more accurately for higher dimensions.
That's actually a very good question. So the problem is, for different parcellation approaches, no matter is like a gradients or soft parcellations or hard parcellations, which is the most optimal dimension is always a problem, remains like unknown. So as a recent paper from Gail Varacross group have shown that actually different parcellation approaches favors different dimensionality for different parcellation, for different behaviors. Therefore, like we do plan to like, so in this analysis, we only include like a different dimensionality for the ICA because it's available from the HTTP dataset. So we do like a plan to include first more gradients, because in this example, in this experiment, we only use 5 gradients, so we plan to extend more. But that require a better like a matching algorithm to align the gradients across subjects, like because the individual gradients are called like a variable across subjects. And another thing is we also plan to include more dimensionality for the Schaefer parcellations and my parcellations range from like around 100 to 1000. So that's actually very interesting to look into actually. Thank you for the question.
Can I just follow up on that question a little bit? So one question I had, because when I was thinking about this, was whether, do you think it would be possible? One of the most interesting things about gradients, right, is partly just they give you a really nice whole brain pattern describing relationships between areas.
Right.
And I'm just wondering whether or not using your approach, you can kind of take the hard parcels and at the end be able to recover a kind of whole brain map that, and then see how much they look like gradients, I guess was my question.
Oh, interesting. Yeah, we can look into that actually.
I mean, I think one of the, I mean, because one of the most interesting things about gradients might just be that, you know, there's the way we calculate the maps, but there's also the consequence of the multivariate relationship between all the parcels, basically.
Right.
I just wonder, basically, using the technique that you're doing, whether it would be possible to sort of like at the end recover a map and work out what type of whole brain distribution of nodes you have that are so predictive. Because it feels like that, you know, is also an, you know, like I think separating it from the technique of calculating gradients and seeing the whole brain relationships between brain systems, for example, is quite a useful or interesting.
Right. Yeah. That's actually quite interesting to what Yiting has done. So, for example, is it possible to apply her techniques into the cerebral cortex regions? That would be like fantastic.
Yes, exactly. Okay, so there's another question from Nicole Eichert. Is it possible to derive spatial information about the similarity measures to determine the brain regions where hard? She just said what I said. So the question from Nicole, I think, was the one I just asked. Can we look at the whole brain path?
So there is another like we have a recent paper already, like the preprint is maybe released this week, I think. I hope my colleague do it fast enough. So we have this fancy approach that can took from nice paper that can invert our prediction model. That we can see like how different, like which functional connectivity edge is important for a specific behavior. So in this way, we can like compare using different parcellation atlases or like comparing gradients versus parcellation to see like for specific behavior, which like which regions, which functional connectivity edges are more important for this parcellation versus weakly for the other parcellations.
Nice. Okay. I think Maxwell Elliott has asked a question that we've probably all talked about a little bit, which is just, again, the difference in the dimensionality between 5 gradients and 400 parcels. And I think the last question is from Boris, who says, nice talk, Ruby, were individual gradients pre-aligned to gradient templates?
Oh, sorry, I just muted myself.
That's okay. I think if you use BrainSpace,
yes. Sorry. The individual gradients are pre-aligned to the what? I'm not sure what is pre-aligned to. So we compute the gradients separately for each subject, and then we use the alignment algorithm, the Prokosty,
yes,
to align the gradients with the group level gradients we obtain using HCP datasets.
Okay.
And the HCP dataset was based on MSM all cortical surface pre-alignment of the features, possibly,
what?
right?
Sorry?
The HCP features, the functional features that were surface registered using MSM all before.
Yes.
Okay.
Yes,
thanks.
we're using the MSL. Yeah.
Okay, and then there's a quick question from Sophie. Were the subjects all unrelated? I guess that's...
No, they are related, but when we do the prediction model, we take care of the family structure so that the families, so if the subject belongs to the same family, we don't split it into the training and test fold.
See, okay.
Right.
Okay, so where are we with time? Got to open a Word document, find that out. Okay, so Lorenzo is next, but we're very early for that. No, it's just about to start.
Spot on.
Spot on time. There you go. Trust the cognitive people to keep to the time.
There we go. Hi, and thank you for the opportunity to present at this workshop. My name is Lorenzo Cacciari, and I am a physician scientist now undertaking postdoctoral training in Dr. Danny Bassett's lab at the University of Pennsylvania. Here, I will be presenting some collaborative research we've been undertaking among UCL, Penn, and the MNR with Dr. Boris Bernhard, focusing on the neurocorrelates of cognitive dysfunction in focal epilepsy. And I'll be showing you how a multi-scale approach, including functional gradients, can be brought into the equation. So, For those who may not focus on epilepsy, epilepsy is a common disabling neurological disorder consisting in recurring seizures and is a very heterogeneous family of disorders. Here, I will focus on the two most common focal epilepsies, i.e. epilepsy types in which a focus, a hotspot of seizure onset, can be identified, temporal lobe epilepsy, the most frequent epilepsy type overall with seizures arising from the hippocampus, and frontal lobe epilepsy, FLE, so that was TLE. This FLE is slightly less frequent with seizures arising from frontal lobe locations. Cognitive dysfunction is a potential complication of any brain disorder, and epilepsy is no exception. So impairment of cognition is very common and can be more burdensome than seizures. A long-held view posits that the core pathological change, so whether the seizure focuses, for example, frontal or temporal, determines the associated cognitive profile, memory impairment in TLE and dysexecutive traits in FLE. The matter, though, as we may understand, is slightly more complicated with more widespread patterns of impairment that may be largely shared. And coming to the neurocorrelates, so getting deeper into what matters to us here. So the neurocorrelates of these cognitive profiles, most cognitive fMRI work in epilepsy to date has used activation maps, so GLMs, general neural models, and to a lesser extent connectivity, showing frontotemporal alterations during language or memory in TLE. But our understanding of cognitive network organization in other epilepsy types, such as FLE, is very limited. So how can we address this lack of knowledge, and how can we advance the current level of evidence in the field? So this being our starting point, now I'll be showing you some results of an investigation of task-related functional repertoires in a poorly characterized epilepsy type, FLE, along with comparisons aiming to disentangle differences between FLE and the most frequent, better characterized epilepsy type, TLE, to establish some sort of functional cartography of cognitive function across focal epilepsy, so in disease. And I will try to show you why we think that functional gradients may help us. So we start with neuropsychological tests, and along with 4 fMRI tasks, 2 language and 2 working memory tasks. For language here, I will focus on 2 clinically applied verbal fluency and verb generation tasks, both eliciting robust frontal lobe activation, and then particularly for the verb generation task, also lateral temporal activation owing to the semantic component. For working memory, we employed 1 verbal and 1 visual adaptation of the N-back task that I'm sure you may be quite familiar with. Both tasks elicited the typical frontoparietal activation along with the activation of the midline DMN. Having introduced our rationale and sort of questions, here is what I think is the most exciting and relevant part of this talk, our methodological framework. So I mentioned a multi-scale functional mapping approach. So we start here, as most of us presumably would, by analyzing voxel-based task activation maps, so general linear models. Then, taking a wider perspective, we decided to summarize task activity patterns in the form of beta weights across 7 canonical functional networks, the 7 Eo-Crean cognitive systems. Then, inspired by recent developments, the object of this workshop, that allow capturing gradients of functional brain organization, we envisioned a third approach. We decided to profile task-related activity onto the principal functional gradient, depicted here and first described by Daniel Margulis and collaborators, and I'm sure by this time you will have heard about it today. And this gradient basically illustrates a continuous transition from unimodal sensory areas on one end to higher order transmodal regions, including the DMN, so DMN areas at the opposite end. And it's supposed to reflect the hierarchical principle of whole brain connectivity. So for our analysis, we derived the principal functional gradient from resting state HCP data, then divided the gradient into 20 consecutive sections, so gradient bins, in line with prior work. Then task-related beta weight maps were aligned and basically overlapped onto the principal gradient, followed by a quantification of task-related signal per gradient bin. In doing this, we were inspired by a couple of really neat functional mapping studies in healthy volunteers by Dr. Smallwood's group, briefly shown here, that basically highlighted feasibility and the added value of mapping task-related changes along the principal gradient in the context of working memory, experience sampling, and perception decoupled cognition. And I highly recommend reading these if you wish to know more about what motivated this line of research. So, coming back to our multi-scale approach, one may ask why these three scales and why profiling task-related activity along the gradient? So using an approach that spans from voxel-wise findings through networks to a gradient-based stratification of findings, we think that these three scales basically offer a local to global translation framework, like three lenses with different magnifying power, through which one can perhaps more comprehensively map cognitive activity, and in our case, as we'll see, better explore differences between health and disease populations. Gradient-based profiling in particular may offer a compact way to represent task-related activation and conceptualize this in the context of a macro-scale organizational principle and cognitive hierarchies more generally. So as a side note, this approach is not exactly in widespread use in the field I come from, so I'm mostly an applied scientist, but I hope this may help us broaden our knowledge of the downstream implications of epilepsy with regards to cognition from a more global, more of an ensemble perspective, if you like. So, back to our study. In addition to 52 controls, we recruited 56 patients with frontal lobe epilepsy, FLE, and 64 with TLE. So these are among the largest cognitive MRI samples in epilepsy reported. Patient groups, I'll be going quickly through the slides. The patient groups were comparable for clinical variables. We controlled for age and sex in all group comparisons. And FLE and TLE had basically weaker performance than controls in all our cognitive measures used that tap into verbal language processing, as well as working memory and executive function. Differences between TLE and FLE were found for naming, that was weaker in TLE, and for mental flexibility and executive function test, that was worse in FLE. Working memory task performance was equally impaired in both groups. So now I'm going to a bit of a results section, and I'm going to provide you with some examples of our functional findings. Starting from language and the verb generation task that has an active control condition, at the voxel level, we observe left lateralized frontal and lateral temporal, left lateral temporal activation. This is all left lateralized in view of the semantic component for the temporal part. Task elicited changes align broadly on eosystems with stronger effects on the frontoparietal, then ventral tension, dorsal tension network, as well as the DMN, and then limbic systems. What about gradient-based profiling? So if we map task-related changes on gradients now, what we see is this undulated curve with basically positive activity shifts at the unimodal end for visual processing, and then starting again at an intermediate location on the gradient, implicating perceptually guided areas, and then going all the way towards the transmodal end. Patient groups activated language areas less well, but changes seemed quite frontal and fairly localized in FLE, whereas profiles were much less favorable in TLE compared to controls. And in fact, we found reduced occipital temporal and parietal activity when TLE was directly compared to FLE. So now, moving on the canonical network framework for group comparisons, we saw greater deviations of network activity from normative values in TLE, orange here, while FLE in red looks somehow more similar to patterns in controls, which is basically what the black heptagon here corresponds to. This shows you reference values and controls. Also, we can see significant differences between TAD and FLE across these three task-positive networks, the frontoparietal, dorsal attention, and ventral attention. So as for task activity profiling on the gradient, here depicted as deviations from the norm in patient groups compared to controls, we know changes that are quite evident in TLE, but not so much in FLE, I should say. In TLE, these involve a wide intermediate to transmodal portion of the gradient that corresponds to the one exhibiting significant task-related shifts in controls. And in terms of differences between patient groups, we know a couple here per gradient bin. And as a global measure, we conducted permutation-based comparisons of this area between two patient curves that appears significantly larger than expected from a null distribution. Then I'm providing you with one example for working memory, that both visual and verbal tasks elicited largely overlapping patterns across the three scales. So starting here, we see the typical frontoparietal working memory activation, along with deactivation of mostly midline DMN. That translates to activity shifts on dorsal attention and frontoparietal cognitive networks. And for gradient stratified findings, a profile that is overall qualitatively similar to that seen for the language task, but perhaps with more marked upward shifts. So with positive activity shifts, starting from, again, an intermediate location on the gradient and going towards the transmodal end. In patients, we found reduced frontoparietal activation and failure to deactivate DMN areas in FLE compared to controls, and even more marked changes in TAD. Analysis on your canonical networks highlighted deviations mostly of dorsal attention and frontoparietal network activity in FLE and in greater contractions in TLE, and significant differences between TLE and FLE for dorsal attention activity. Profiling differences along the gradient showed slight but evident global deviation of task-related recruitment from controls in both FLE and TLE. Most visible here for the intermediate gradient portion. Here, while we do not find differences between patient groups for specific gradient bands, permutation-based testing on this area between patient curves highlighted, so indicated larger values than expected from a null distribution. So finally, last item, I'd like to briefly report some associations between task-related changes across our three scales and inter-individual differences in cognitive performance, as I presume this aspect may be of interest to a wider audience. So if we start with language, here on the left is an example of an SPM-based linear regression on language activation and expressive naming scores that at the voxel level shows fairly localized inferior frontal and lateral and basal temporal effects. On your systems, however, correlations were more evident for the limbic network. And on the gradient, we have this quite interesting pattern. So what this plot is showing here is per gradient bin, the strength of the correlation between task activity within each bin and cognitive performance. So we have some subthreshold positive effects for the intermediate gradient portion and an uncorrected negative association between naming performance and activity in the last gradient bin. So bear in mind that these results are preliminary, but I thought they would be worth sharing with you all. Patterns were more interpretable here for this topic at all scales for working memory that may perhaps be more amenable than language to be studied from a network perspective. And we see, in fact, quite evident associations between digit span scores and end-back activation for a set of regions that nicely recapitulate the working memory network here. And these are mirrored by significant effects seen for the frontoparietal, dorsal attention networks, and then to a lesser extent also for the DMN. for effects on gradients. So you can see here how task-related signal in the intermediate, transmodal gradient portions exhibits significant correlations with working memory, so digit span scores. And as an example, the scatter plot here on the right shows you the data distribution for the correlation between digit span and task-related activity at the 16th gradient bin. So to give a final overview and to bring back some of my earlier points, I hope that this talk conveys the message that our complementary and multi-scale analysis can track the neurocorrelates of cognitive function and dysfunction from a local to a network base to a more global whole brain organizational scale via gradient mapping, and collectively may provide a comprehensive approach for mapping cognitive function in vivo. So gradient-based profiling in this context may help us conceptualize patterns of function and dysfunction within a framework that more closely relates to macro-scale organization and brain hierarchies. And in this case, it ultimately helps us advance knowledge of the broader cognitive implication of focal epilepsy syndromes. We apply this framework to address some questions of clinical relevance. So studying a well-known epilepsy type, TLE, and another one we still know very little about, FLE, and we showed a relatively large-scale disorganization of cognitive network activity in FLE as well as TLE that affects both perceptually guided, so attentional, and transmodal systems, including the DMN, that exhibits this pattern of altered deactivation. These profiles are overall shared across syndromes and potential targets to further explore network vulnerability across epilepsy types. Changes, however, particularly for verbal tasks, appeared more severe in TLE and on balance, on a spectrum ranging from no differences to maximum differences. I'd probably place my pointer around here. This study, of course, was a team effort, and I would like to thank my great mentors, Boris, Dani, and Matthias, for the support in this project, and my colleagues and collaborators for their contributions, and quite a few funders, including the NIH, for supporting my postdoc. And thank you all for listening. I hope that was of interest, and I really I look forward to your questions.
Okay, that was a great talk. I've actually got a question I would quite like to ask, if that's possible. Lorenzo, are you here?
Yes, of course. Yeah.
It's just an observation. It looks like you're mostly dissociating based on the middle of the gradient, really.
Mm-hmm.
And I just wanted to point out that in the decomposition that we get that gradient from, there's actually another gradient, gradient 3, which basically resembles like the deactivation default mode network does.
Yeah.
And I just wondered whether it might be useful actually to try running the same analysis you're doing just now, but using gradient 3 just as a bit of a contrast, because you might find in that case you're actually dissociating the ends of the gradient a little bit more. Because basically when you see a peak like that where the middle is high and it's tailing off in the default mode ends, that might actually be gradient 3 that would map better.
Yeah, no, absolutely. This is, not sure if I lost you, but yeah, this is a fantastic point. And I think when we first started this, I think we went for gradient 1 being, the most popular, and given what we were getting from the task maps. And now looking at the results, interestingly, I was looking at, gradient 1, 2, and 3 in the last few days and looking, we really need to look at things more deeply. And the idea about gradient 3 is like ongoing. So I hope to be able to present some analysis in relation to that fairly soon. So yeah, it's I totally agree. It's a fantastic point.
There's a paper that we've just published in Scientific Reports where because you can kind of imagine if you wanted to express all of the task data in a space, you can actually make a 3D space out of all the different gradients.
Yeah, that would be actually, it's one of the future directions actually, now that you make me think of it, because I was thinking for language, for example, on the other hand, it would be also helpful to have data plotted also on gradient 2, because particularly for particularly for the verbal fluency and the verb generation tasks they're not maybe the best language tasks, but we've taken those from a clinical context. So they're used to lateralize language in our patients. We have more of a sensory sort of sensory motor activity that I think was kind of evident. I skipped through it quite quickly, but it was a bit evident in the stratification. So having the three of them in a 3D space is like the dream. So
yes,
yeah.
So check out a paper in Scientific Reports that came out today. Adam Turnbull. I tweeted about it if you follow me on Twitter, but if not,
yeah. No, thanks. I appreciate this, and it's good that things are evolving so quickly. It's so inspiring. Thanks.
Okay, so some talks. So one question is by Eduardo, and he's just asking, is there a paper?
No, we're working on it, so I hope to be able to share a preprint with you soon. It's in the final stages, hopefully, so it's coming. Watch the space.
Okay, and then from Boris's question, which is, are there differences in left versus right TLE and left versus right FLE? Are verbal deficits and associated functional anomalies more pronounced in left lateralized patients?
Yeah, that's a very interesting point. So I think to answer quickly.
Well, I didn't want to ask about medication, so
yeah, thanks. That's the second favorite point. Yeah, so I mean, also to give a bit of a broader context to the audience that may not, maybe work on epilepsy. So I think obviously with temporal lobe epilepsy, I think where whether the left or right hippocampus is affected determines a profile. And so verbal deficits may be more evident in left temporal lobe epilepsy, but differences on the global scale, so particularly on networks and gradients, are subtle. Left and right frontal lobe epilepsy don't differ that much. And we actually see that sometimes right frontal lobe epilepsy is more impaired. So the two patterns are actually, they differ. So left and right have different effects according to where the focus is, but differences are subtle at the global scale, to answer this question quickly. But I'm happy to elaborate further later if it's of interest.
Okay, so basically, Lorenzo, Simon Keller says, first of all, he thinks your haircut is great. Did you cut it in the pandemic? And he also asked you, were all the patients non-lesional? And he was trying to get a feel of how homogeneous the patient groups were.
Right. Yeah. So So for temporal lobe epilepsy, we actually took those that basically had proven hippocampal seizures, and so they had the typical hippocampal lesions we see. It's called hippocampal sclerosis. It's basically kind of a scarred hippocampus in a way, and so they all had lesions. For frontal lobe epilepsy, as people who do work in epilepsy may know, it's very difficult to get a homogeneous group. So we have a mixed bag of people but the lesions are really small. So we took out the big lesional patients. So yeah, that basically, that's what we have for the frontal. So it's we tried to look at some subgroup analysis, but I didn't have time to report those here.
Okay, and then so one question from Sophie, which is to how can we highlight differentiability within gradient levels along multiple dimensions? I think here she's getting at the possibility that the gradients reflect overlapping patterns in an area of cortex.
Yeah, so yeah, no, I see. That's a very interesting question. I mean, I'm trying to think. Some peninsular regions. I don't know actually if adopting the approach and looking at things on 3 different gradients, for example, and so plotting things in a 3D space may help answer this question. I mean, right now this would be my sort of gut feeling, and to kind of try to dissociate those. But I don't know if Sophie can also perhaps elaborate a bit further in terms of what, I mean, if she has any to discuss.
Yeah. I was just thinking some regions are not so differentiated, such as the insula in the principal gradient, or also the default mode. It is all there at the high end, at the apex, but it is also different, right? If you have a TPJ or frontal region, so maybe
absolutely
like beyond it. But yeah, it also came up already with the discussion with Johnny, and so
then the idea of using, for example, gradient 3 as a complement, particularly for to kind of try and disentangle things a bit better towards the transmodal end may be a possibility to try and go past that. But I also understand that this this may help, but it's not the definitive answer. So I'll give another thought about it. But no, that's a great point, and yeah, point absolutely taken. I totally agree that it's difficult to dissociate effects, particularly in insula or DMN. Yeah, totally. Yeah.
Okay, so there's just one quick question from Gabriel Castrillon, who wants to know: would it be possible to get access to this data set, or are you planning to share after publication of the results?
So that's a very difficult point, because this is patient data that was acquired like at UCL, and we didn't have consent for sharing, but we'll see what we can do. Yeah, and I'm happy to, for people to get in touch with me anyways for this purpose.
Okay, so I just want to say that Todd Woodward has sent a really nice question that we can't ask because we have to move on to the next talk. So maybe if we can maybe think about that in sort of the chat afterwards. So I think the next talk is Alexandros. I think, is that right? Are you here? Okay.
In this presentation, we will occupy ourselves with unifying wiring principles pertaining to different scales and species. Organization of the brain of different mammals is characterized by different levels, different scales of organization. That is, its large-scale wiring or its cytological composition. And recent endeavors have mapped in detail these different levels of architecture. For instance, certain advancements in the field of connectomics have unraveled in detail the intricate wiring of mammalian brains, including the monkey, the human, and the mouse brain. Moreover, projects like the Big Brain Project have mapped in detail the cytological heterogeneity of, in that case, the human brain. Thus, we have at our disposal a wealth of unprecedented data, but certain key challenges remain. Namely, given that we have this wealth of data, what is a parsimonious set of principles that can describe in a numerologically informed way its different scales of organization and uncover potential unifying threads that bind these observations across different species? So this question constitutes the motive of the study that I will elaborate on. Starting point is thus to have these raw observations and aim to distill in a parsimonious manner key components that help us understand the relation between these two different scales across different species. Thus, we have a transition from observations to principles, and the explanatory depth with respect to the scientific object at hand in the mammalian cortex is enhanced when we transition from left to right, as we observe in this diagram. Our starting point is the cytological composition of the mammalian cortex. Studies of decades have uncovered that the cytological composition of mammalian cortices is heterogeneous. That is, we have to do with spatially ordered changes in terms of cytoarchitecture. And these changes can be quantified in different species by using the so-called neural density. This simply means, given a cubic millimeter of cortex, count how many cells inhabit this cubic millimeter. And if we do that in the macaque monkey, we see that we have spatially ordered gradients of cytological heterogeneity. For instance, the entorhinal cortex exhibits very low density, but as soon as we start transitioning towards primary visual areas, and we end up in B1, we see that the neural density becomes higher and higher. So we can quantify with neural density the cytological heterogeneity that manifests as spatial order changes across the cortical sheet of different mammals. the level of connectivity, studies have shown that there is also heterogeneity that pertains to the wiring of the brain. From a topological standpoint, certain areas are more central than other brain regions, and these central areas are tagged as hubs or core. We have a highly interconnected set of areas. In contrast, the periphery refers to areas that are not heavily interconnected with the rest of the brain. So we have to do with heterogeneity, but now at the level of connectivity, at the topological level. The question is, if and to what extent cytology and topology relate to each other across different species. To this end, we map cytological gradients in different mammals. Specifically, we map these gradients in the mouse, the cat, the macaque monkey, and the marmoset monkey. So we have a variety of species, carnivores, rodents, Old World and New World monkeys at our disposal. By doing so, the next step is to use the extensive wiring diagrams that exist for these species and uncover the more central regions in each one of these species. That is, the goal is to uncover the core periphery structure in these different mammalian species. So, it's denoted here with this color and the periphery with this color. And once we have mapped these topological features in different species, the goal now is to relate them to the cytological composition of the areas. And as we see here, in mice and marmoset monkeys, topology does not lead to a statistically significant segregation in terms of cytology. That is, there's no statistical difference between core and periphery areas in terms of the neural density, the cytoarchitectonic status, that is, of these areas. On the contrary, in cats and macaque monkeys, we observe a cytological segregation of core and periphery areas. And the segregation entails that central areas, the core areas, have a lower neural density when compared to periphery areas. That is, the core areas encompass the parts of the cortex that are less densely populated, less cytologically differentiated with this. So we have to do with a specific manifestation of a principle that relates topology and cytology in mammals. What could be the ramifications of such species-specific relations of cytology and connectivity? To this end, we build on observations in the macaque monkey, and these observations relate the cytological status of areas, specifically the prefrontal cortex of the monkey, that ranges from low to high density areas. And the study relates these neural density variations to myelin content of areas. And as it's here depicted, the less cytologically dense areas also exhibit low myelin content. And this stepwise gradual increase in cytological composition neural density is accompanied also by an increase in the overall myelin content. So that means more myelin is equal to higher levels of neural density. And from a functional standpoint, this relation helps us understand the degree of plasticity of these areas, because these gradients of cytology and myelination are also entailing changes in terms of the plasticity of each region. For instance, high plasticity is accompanied by low neural density. In other words, the more myelinated and the area, the more myelinated an area is, the more neurally dense an area is, the lower the plasticity of that area is. With these observations now, we can have potential functional ramification of the phenomena that we observe. That is, the displacement of the core that we have observed in our own studies is now interpreted in terms of plasticity. So we have to do with an increased segregation of core and periphery in terms of cytology as we transition from mice to marmoset monkeys, cats, and macaque monkeys. And this cytological segregation now also entails, in light of the findings that we have previously iterated, that the network core in the cat and the macaque monkey also encompasses the more plastic parts of the cortices of this species. In summary, we have a species-specific alignment of the cytological and topological gradients in the mammalian cortex. And when this relation is pronounced, we have to do with a more central, less dense principle. This displacement of the network core in the mammalian spectrum indicates that all foot monkeys and carnivores may exhibit a network core that is heavily interconnected areas that also encompasses the more flexible parts of their cerebral cortex. And this might have implications for flexibility and adaptability to niche, for instance. And with that, I would like to thank you, and I hope you found something of interest for your own endeavors.
Great. That was an excellent talk, Alexandros. So there was one question which I think you've actually answered, but I think it might help if we just basically go through it and you answer it for the audience, which is, are the core and the periphery functionally similar across the species?
Hi guys. Yes, as I wrote down in the chat, this is not the case since in the mouse cortex, the core areas encompass also parts of the somatomotor cortex. So if you check the maps, that's visible. So this is the reason why also the cytoketonic gradients do not align with the topological gradients in mice and maybe in other rodents, but yeah, we don't have data for that.
Awesome. I mean, I had a question, which is, how do you, what implications do you think for this changing in the core has for the different concepts of hierarchies that we might imagine these patterns reflect?
Hierarchy, it's a classic question that I ask to people. What exactly do you mean by hierarchy? Because it has different meanings.
At least 4 meanings by a recent paper I just had to read.
Sorry?
It has at least 4 meanings by a paper I just read.
Yeah, exactly. So yeah.
I just thought it might be useful to unpack that idea, how that kind of works in this context.
So if we take into account the hierarchy as kind of synaptic steps from the sensory periphery, so that's one definition and one kind of use of this word in the community, then what these results indicate is that actually the periphery, in a way, is already the core in the mouse. So the somatomotor cortex is already reaching the core. Contrary to what we know in primates or in the human brain. So the classic work from Mesulam and what other people have done in more recent years. Or like in the macaque monkey, what Jones and Powell have shown in the 1970 paper. So that means that actually it could be the case that the sensory input in the mice does not have, let's put in quotes and we can break it down, so many transformation steps as they proceed from sensory to multimodal to the core, to the so-called apex, as Daniel et al. Calls it. So it's already reaching the core. And this might have to do with, in a way, multimodal integration, but that's kind of a speculation. We have a modeling study, but it's not already out. The idea is that if you have sensory input that does not get filtered, let's say, through multiple steps, then you have less integration, let's put it in many quotes, compared to a situation where you have that and everything meets, let's say, from the different modalities into a central core.
Yes.
Yeah.
Presumably that can, so I mean, I guess like in a very loose way, that might relate to the complexity of the behavior that an animal can engage in, maybe.
That is one thing, absolutely. And the other one that is a bit more tied to the results that I concretely present. So we have a more concrete basis to have, let's say, more informed guesses, let's say, is the fact that the core, again, like in mice, does not encompass the more plastic regions. So it could be the case that this, it's not nice to say about mice, but if you ask people that work with them, they always say that, oh, mice are stupid. Anyway, so poor mice. But compared to rats or like primates, I mean, they say, oh, they learn much faster and so on. That's kind of an implicit assumption that many people have, that mice are a bit more hard to train and less flexibly, let's say, orienting themselves in a new environment. So on relative terms, I'm not saying that mice do not learn and they're not flexible.
Awesome.
Yeah.
So are there any other questions for Alexandros? Your voice is better.
All right, so I go back to the non-mute, non-video mode. Thanks a lot. Bye.
I think there's basically maybe next, I think it's the general questions and answers. Is that right? What time are we? It's yes. So I'm moderating the session. So that requires questions. So I'm looking in the chat stream. I mean, it's been an interesting set of talks because they've all addressed gradients in quite different ways. There was Shoei's paper that looked quite closely at the mapping between the principal gradient and then a lot of different things. I guess one of the overarching things that might just be good to think about would be the extent to which we can really think about the gradient maps, which we get somehow from functional connectivity data at rest usually, as having some broad implication for the way that behavior is organized. I mean, I think personally that's one of the more interesting, I mean, obviously gradients are very interesting for all kinds of reasons, and but I think one of the more interesting implications of them are the possibility that they are telling us something about the templates that the brain uses to perform different actions or cognitive states, I guess. So I'm just wondering whether if any of the speakers from the session are around, they could maybe give their thoughts on the different degree to that would be supported by their data. Do we have any speakers? Shoei? Ruby? Lorenzo? Lorenzo!
Yes.
I mean, just to maybe to concretize this a little bit, I think one of the things that's interesting when you begin to try to understand the brain in the terms of a context is we know that when we look at tasks, they have different motifs. And so one of the interesting things I think that's beginning to happen in imaging, which probably goes back to quite a lot of early work, which showed similarities between resting state motifs and task states. So that sets up a very deep symmetry between a situation when, when Biswell demonstrated the connectivity of the motor system at rest, looking like the act of finger tapping, and that sets up, in my mind at least, a very, really deep question, which is, how far can we take the idea that the patterns that we see that reflect the organization of the brain at rest actually have implications for behavior? So what do you think, Lorenzo?
Well, yeah, I mean, I think it's, yeah, I mean, it's like standing on the shoulders of the giants here. So, I mean, but I'm happy to, I think to summarize, I think the concept that you just outlined was actually the motivating sort of question behind this idea of implementing, multiple scales and trying to understand the organization a bit better. And so I think in this context, I think using gradients here is an example of how we can bring this further from, just, either a boxer-wise or some resting state network to look at things at a bit of a higher level. So to give a bit more of a hierarchical context. And so in my view, I think trying to apply the method, I thought that we can achieve this if we use gradients. And I showed one example in my talk, but obviously as we discussed, I mean, it would be nice to plot it against, for example, the 3-verse gradients. But the concept is that, yeah, it's a way to move things up and to approach, a task mapping. And so what cognitive activity implies in terms of brain sort of responses to a higher level. And so, yeah, I totally agree. And I think that's why I kind of pursued this. And I think that's why, I mean, I'm not the first one here. So I think we looked up to also what your lab has been doing. And so I totally sort of agree with this point. And I hope that others, if they want to chip in and they can chip in, can sort of, confirm this if everyone is in agreement. And I'm sure there may be also other ways, but I found the gradient tools as a really convenient one to do this. That's what that is.
Awesome. And Alexandros, are you still here?
Yes.
I mean, one of the questions that I think I've asked this question repeatedly throughout this session, but one of the things I'm really interested in is just how you can recover flexible patterns from the anatomy. And I was wondering whether you're, like at some level, at a zoomed out level, it looks like the brain switches around what it's doing, depending on the context. So, like different cognitive states are supposed to have different patterns. And in a way, that you encounter a kind of problem if you take that idea far enough, which is just that you kind of run out of brain regions and or things people can do. And hierarchies are a solution to that in various different ways, because first of all, they can be overlapping, which I think is helpful in that regard. The second one is they question what the function of the hierarchies would be in this context. So I think, for example, when I read your paper, actually, it was really helpful to me because it kind of characterized different ways that hierarchies can influence a dynamic system without it necessarily being the case that at the top is a abstract representation, for example. I don't know if you'd be able to comment on that for about 3 minutes before the next session.
It's a lot to unpack, but very briefly, like I forgot the paper, but I'm sorry for that, but I can send it to a common channel or whatever later on. You can assess actually the, let's say, structural underpinnings that equip regions to be flexible, let's say. Because we know that, for instance, certain, even in classic examples that they are not centered around gradients, for instance, if you do a analysis of the moment-to-moment fluctuations of the resting state signal, then you can see that many regions are more flexible in the sense they change their affiliation with different networks at different time points, and others don't. That's kind of a rather recent observation. So now the question is to say, okay, why is this the case? Because that's an observation. But of course, to understand it like at the deeper level, we have to say what heterogeneities at the structural level might equip these regions in order to do that. And now that we have detailed multimodal data, for instance, in terms of the transcriptome and myelin and so on, you can start unpacking this. And I'm pretty sure, for instance, if you go to the Allen dataset and you dig out genes that code for plasticity-related proteins, and then you have this signature for different regions across the cortical mantle, then I'm pretty sure that an association will emerge between flexibility, in the context that we just discussed about it, so swapping membership in networks, let's say, and expression of the genes that code for this type of proteins that are relating to plasticity. Yeah.
So do you think basically there's a possibility then that there's a kind of genetic, I mean, probably Sophie might have something to say about this, but a kind of genetic, the way that the brain flexibly change its organization?
Yeah, I think so, because otherwise, what facilitates it? I mean, there must be something, I don't have the answer of what exactly is the case, but if you don't find this in the other levels of dimension of the cortex, then we run out of places to look at that.
You think it can be just done by magic?
Yeah, that's another option. I
think we should just use magic to explain it, and then,
Yeah, because that's the important bit. I mean, sometimes we have great observations, and of course it's a starting point of everything to observe something. But then this shouldn't be considered as the, let's say, end of the endeavor. Because currently in the field we have many observations, but
few principles. I mean, you cannot boil down to say, okay, when it comes to cortical organization, how can I boil down all this multimodal complexity? Can I enumerate 3 principles, 4? Okay, what is the case with the cerebral cortex? It is obeying this principle, that principle, and so on. So that's something, I mean, that's a more general comment, but I think it relates also to what you said. Because then you will really understand and tie down into concrete features all these functional aspects that cognitive neuroscience is interested about.
Yes. Awesome. Okay, right. So what happens next? He says, looking at his Word document. Break 2 begins.
Yes. So thank you, everyone, for the outstanding talks and for the great discussions. Thanks to the chairs for stimulating this. So I'm having a really great day so far, and it's really nice. So now I want to make one announcement. So with Daniel, we decided to make like a mailing list, a Google Groups. So, and you'll receive an invitation for this. And then you can decide, then you can join the group. And this will be about articles you want to share, job postings, everything surrounding gradients. So the Google group is called Gradients at Google, I think. And now we go to the second break. And during this break, we'll have a musical performance by the project from Johnny and Rob Leach.
Is Rob here? Rob's here or not? So technically, it's not actually by me or Rob. It's by some mystery characters called the Natural Philosophers of Attitude, who recently got terminated by Twitter for reasons that we don't understand. So I was planning to use, they were planning to use this experience to generate followers on Twitter, but the weekend made that impossible. But they did want me to stress that they have a website, naturalphilosophers.com, that so far has not been shut down by the man. So you can still check out their fantastic work there, I believe. Okay, so.
And we'll restart proceedings on the hour, by the way.
Okay, perfect. The video isn't that long. I don't think the Natural Philosophers are that long.
That's okay.
That's okay, good. There should be music at this point, I believe.
Yeah, the audio is not working.
I'm calling Sasha for the sound. Sasha? Sasha?
Yes.
Can you restart the video? There was no sound. Thank you.
Beats on our beats. You got to show me unbreakable beats. These beats on our beats. You got to show me unbreakable beats.
Okay. Okay,
Yeah,
so
we will say thank you to the Natural Philosophers of Attitude for passing that on to Johnny so he could play it for us.
yeah, no problem. And I can also pass on everybody's good wishes, and hopefully Twitter will allow them to take it. Currently, there's an issue.
This got more responses than any of the talks did, I think, on the chat. That's saying something for sure.
Yes. Well, you know, Twitter have decided to suspend our account, so
That's so bizarre.
They feel the competition clearly.
I think so. I mean, you know, there's like an open market for brain-related jokes we discovered, and obviously someone's trying to close it down. Okay, so what's next in the program?
Yeah, so that was really great. Thank you very much to the artists for the show. Okay. And the next session is going to be our last scientific session, and it's going to be moderated by Casey Pacola and Richard Bethlehem.
Oh, thanks, Boris. So I think I'm taking the first bit at the sadly last session of today, where we have an interesting lineup of speakers talking about, amongst other things, gradients and how they intertwine with genetics. And our first speaker today is John Murray, who's an assistant professor of psychiatry, of neuroscience, and of physics at Yale. So clearly the full package to talk about gradients today. And I believe, in addition to just talking about genetics and And gradients, he will also talk a little bit about like a statistical framework for testing some of these things. And I think this has come up in a bunch of earlier talks today. So for those of you who sort of questioned Reiner about some of the parcellation stuff, I think John Murray will also address some of those points. So without further ado, I think, John, floor is yours.
I'd like to thank the organizers for the invitation to participate in this event on gradients and brain organization, and the audience for your attention. My name is John Murray. I'm an assistant professor at Yale University with appointments in psychiatry, neuroscience, and physics. And I direct a lab which focuses on computational neuroscience. And so I'd like to describe two studies today from my lab. One on developing large-scale circuit models of large-scale brain dynamics, such as resting state functional connectivity, and the applications of those to study the effects of pharmacology on large-scale brain dynamics. With the specific test bed here, looking at a data set of resting state fMRI under LSD administration. And the second study will instead be on statistical modeling of large-scale brain gradients and maps, and how we can apply those to statistical analyses of gradients in neuroimaging. In particular, applications to brain map comparisons and gene set enrichment analysis. Okay, so a large motivation for my group is trying to bridge levels of analysis. And so, for example, when studying neuropsychiatric disorders, we're especially interested in symptom variation at the level of behavior and how that may be influenced by molecular alteration in therapeutics, which happens obviously at the level of receptors, just huge gap in variation. And so we can try to kind of piece in these levels of analysis to create mechanistic bridges. And so there's obviously huge literature developing neural biomarkers using functional neuroimaging to establish what are the patterns of neural features, be they maps and networks, which relate to symptom variation. Still a large gap to level of molecules. And so we can kind of bridge that from the other direction. And my group and others are looking at mapping of gene expression and transcriptomics to look at the brain-wide distributions of different genes implicated in different pharmacological and disease processes to try to derive neural maps, which can be related to neuroimaging. We can bridge this gap even further by doing pharmacological neuroimaging with causal perturbations of the molecular systems and observing the impact on large-scale brain networks. And then we can make those mechanistic links more computationally rigorous by simulating dynamics in large-scale biophysical modeling and simulating the effect of pharmacology on given receptor systems and simulating the effects on large-scale brain dynamics, which in turn we can relate to neuroimaging. So the way this would look like is we're going to take this large-scale model derived and constrained to resting state fMRI, for instance, and we're going to simulate at some level of resolution excitatory inhibitory neuron interactions within a local microcircuit. And we're embedding that circuit within a large-scale network. And then to simulate the effect of pharmacology or molecular perturbation, we can use gene expression mapping, such as from the Allen Human Brain Atlas, to drive what the topography of the receptor densities are using the gene expression pattern as a proxy to simulate differential strength of perturbation via systemic pharmacological manipulation across the brain. And then we can also be informed by slice physiological studies to gain insight into what are the cell types and receptor sites implicated in particular synaptic or receptor alterations. And so we can then use this framework to simulate differential predictions for neuroimaging, be it fMRI or MEG, and test and constrain the model hypotheses. And so the test bed that we're going to be using here is a data set collected by our collaborators in Zurich on resting state fMRI with LSD administration. And our measure is going to be what we call global brain connectivity, which is merely the mean functional connectivity of an area. And what we see when we compare LSD to placebo is a very interesting topography across cortex of the change in GBC, in particular this large increase in visual cortex, which you see here. This is a very unique data set because what they found is that they were able to completely block both the neural and the behavioral effects of LSD by pre-administration of catanserin, which is a more selective antagonist of the serotonergic 5-HT2A receptor. And so we can see that here when we compare LSD to LSD plus catanserin, we get something very similar to the placebo condition. And so this gives us a very strong hypothesis for bridging from the systems level of neuroimaging to the molecular level. And that's that this neuroimaging map from pharmacological imaging should align with the gene expression topography for the gene HTR2A, which codes for the 5-HT2A receptor. And so when we compared this pharmacological imaging map to the gene expression maps derived from the Allen Human Brain Atlas, what we found in line with our a priori hypothesis was that the HTR2A map had the strongest positive correlation out of a set of implicated genes, serotonergic and dopaminergic. And we can again compare that to the distribution across the full range of genes in the Allen Human Brain Atlas for comparison. And so what we'd like to do on the modeling side is try to directly simulate the effect of the drug in a biophysically based model and see whether we can recapitulate the neuroimaging effects observed at the systems level. And so we have this model with excitatory inhibitory neurons embedded on each node. The interactions between the nodes are constrained by a structural connectivity matrix derived from diffusion-weighted imaging. We simulate synaptic and hemodynamic time series to create a simulated bold functional connectivity measure. And then we can simulate the effect of LSD through the 5-HT2A gene, the HTR2A, 5-HT2A receptor, by relying on physiological studies which implicate neuronal gain and the transfer from input current to output firing rate being a neuronal site of modulation by this receptor. And so we can do this differentially onto excitatory and inhibitory neurons and have the strength of the gain change follow the topography of the HTR2A gene derived from the Allen Human Brain Atlas. And therefore the strength of modulation follows that topography. Finally, we can then get a simulated functional neuroimaging measure, in this case, the delta GBC, and compare and fit that to the empirical measures. And so we have two free parameters here in the model, which are the strength of gain modulation onto excitatory neurons and onto inhibitory neurons. And we can then look within this 2D parameter space and see how that impacts the fit of the model delta GBC to the empirical. And what we found is that the model gives the best fit to the empirical when there is a net positive fractional change in excitatory inhibitory ratio, indicating a larger increase in gain preferentially onto excitatory neurons relative to inhibitory. And that is consistent with some more detailed physiological studies of the effect of the 5-HT2A receptor. So that's one conclusion consistent with the prior literature. And now we can look at what these topographies are. We have the empirical delta GBC, the best fit simulated model delta GBC, and we can get a nice fit to this cortical topography. And one really interesting thing is comparing this back to the gene expression map alone. And what we found is that whereas the gene expression map alone to the empirical map had a fit similarity around 0.4 something, here we're able to get up above 0.7 by actually simulating the neural measures which are being fit to in the dynamical circuit model. And so this suggests a framework of how we can bridge all the way from the molecular to the systems level by simulating neural dynamics and simulating the topographic patterns of receptors and their differential impact on different brain regions, and ultimately how that affects the brain patterns, in this case at the level of gradients. We can compare that to randomized maps, and it's somewhat unfair to compare our HTR2A map to a randomly shuffled topography, which doesn't look like the smooth gradients that we observe in the gene expression maps. And so these have randomized topographies, but preserve spatial autocorrelation. And then we can refit the model with these different surrogate maps and compare our original HTR2A map to assess significance. Similarly, we can also compare our HTR2A gene to other implicated genes, serotonergic and dopaminergic. And here we found that the HTR2A map not only has the best fit, but also the most robustness of the fit within parameter space. Okay, and so to round this out with the second part of my talk, I'd like to talk now not about biophysical modeling, but about statistical modeling. In particular here, generative modeling of brain maps with spatial autocorrelation, which is preserved or matched to the target map of interest. And so here we may have empirical maps such as T1, T2, or thickness. And if we simply shuffle the values of this map, we get essentially white noise, which is an implausible kind of null hypothesis for testing questions about specific topographies of these brain maps. But this is essentially what the implicit hypothesis is when one does a standard conventional, for example, a Pearson p-value that doesn't take into account the autocorrelation structure. And therefore, we felt that there was a need in the field to instead use these spatial autocorrelation preserving surrogate maps, which can be matched in their spatial autocorrelation structure to the target map, but have randomized topographies and random patterns that emerge. And then use these to generate null distributions for our statistics of interest. And we can, again, kind of fit the spatial autocorrelation structure to the empirical map. And so to give one example of this, if here we're testing whether the T1, T2 map is significantly aligned with the thickness map, our assay-independent surrogate maps or a conventional assay-naive Pearson p-value would give very implausible p-values. But instead, if we use the assay-preserving surrogate maps, we can generate a plausible null distribution against which to compare our target. And for example, here, if we take two random assay-preserving surrogate maps and say, what is the fraction of pairs for which a standard Pearson p-value would give you a significant result, we find here that in 93% of randomized topographies, nonetheless would give you a significant p-value, but in this case, being spuriously driven by the null hypothesis that the maps are completely independent white noise and lack spatial autocorrelation. And so this shows that spatial autocorrelation can substantially bias and drive spurious results in these types of map-map correlation analyses. So I don't have time to go into it here in terms of the algorithm of how we generate these spatial autocorrelation preserving surrogate maps. But you can read about it here in the paper that's in press. And we've released a software package called BrainSmash for generating these maps, which use basically a target map values and essentially a distance matrix between all the elements. And so this framework is very flexible. It can give you maps with full coverage and can be applied to both surface and volumetric neuroimaging data, dense as well as parcellated, and cortical as well as subcortical. And so we think that this may be a valuable tool for the community. And as one final application of how this could be used, I'd like to talk about gene set enrichment analyses. And so these have become increasingly popular in studying large-scale gradients in neuroimaging. And so the kind of standard approach is to take your map of interest, compare it to many gene maps, for example, by looking at the alignment or correlation, selecting the most correlated genes, and then doing a gene set enrichment analysis on different ontology terms to see whether those are significantly enriched for these particular genes relative to a random set of genes. And the problem here is that this does not actually test the null hypothesis of whether these enrichments are being driven by the specific cortical topography of the map of interest or neural topography, and not being spuriously driven by the fact that these maps are smooth and autocorrelated, which in itself might preferentially select some genes over others and drive these enrichments. And so what we propose is an assay-corrected gene set enrichment analysis, which has two steps. The first is deriving assay-preserving surrogates from the target map, and then constructing a set of p-values across the genes for that set of assay-preserving surrogates. And so if we look at that, for example, what we can see is that in this case of spatially autocorrelated surrogates, we actually get significant enrichment in a number of different gene set ontology categories, which are not being driven by any particular topography, but are merely enriched for genes which have spatial autocorrelation themselves. And so you can see the problem here, which is that if one did this on a single map of interest and observed enrichment in these categories, you would not know whether this is due to the specific topography of the map itself or merely due to the fact that it's spatially autocorrelated. And therefore, the second step is to then transform the p-value for the empirical map into an assay-corrected p-value by comparing the observed p-value against the distribution derived from the assay-corrected surrogates, assay-preserving surrogates. And that gives us an assay-corrected p-value. And in this case, for the T1, T2 map, what we find is that many of the enriched categories, according to the traditional analysis, can be explained merely by the fact of spatial autocorrelation, because they are also enriched equally for the assay preserving surrogates. But we can also identify which categories we get a significant corrected p-value for, indicating that this enrichment is preferential for our empirical target map, in this case T1, T2, even relative to assay preserving surrogates. And so we think that this may be a way to prevent the kind of spurious enrichment which may be observed in these gene set enrichment analyses. Okay, so to wrap up, I've described two studies, one of circuit level modeling, where we've tried to bridge from the molecular to systems level, bridging from transcriptomics to circuit network dynamics to pharmacology. Ultimately, we would like to bring that to the level of behavior. And then the second part, describing statistical analyses of gradients and how that can be, number one, spuriously driven by the spatial autocorrelation, which is such a prominent feature of large-scale gradients, and how those can be addressed and corrected through generative modeling of autocorrelation matched surrogates. And finally, that we've released an open access software platform called BrainSmash to facilitate these analyses. Finally, I'd like to thank my collaborators at Yale, in particular the lab of Alan Antichevich, the University of Zurich, and really highlight this is primarily the work of Joshua Burke, a senior PhD student in my lab, as well as thank my funding sources. Okay, thank you for your attention.
So thank you, John, for a really, really excellent talk, really covering lots of different topics there as well. I'm just going to sort of open it up for questions just straight away. I saw there were already quite a few questions in the chat. I'm not sure if you want to elaborate on any of the, like I saw you were already responding to most of the questions, but are there any that you want to elaborate on specifically? I thought the question, like sort of comparing it to spin permutations, is quite intriguing. So maybe you can say maybe a bit more about that.
Talk about it for a minute. Yeah, so I mean, right now the spin test is kind of the de facto way to correct p-values of map correlations. And that works very well when you have kind of a full coverage cortical maps and you're trying to evaluate the significance of the comparison between those. There are some limitations to the spin method. So it works for surface maps. It needs to be like a whole cortex map. You can't do a cortical region and do a spin test on that. It doesn't work on volumetric data, and therefore it doesn't generalize to subcortical structures. And so our method applies to all of those cases. It's a slightly different null hypothesis where you're correcting for the first order autocorrelation structure captured by the variogram rather than the full topography being rotated. But when you're looking at just the map correlation, they basically give similar p-value distributions. But the main utility is, I think, in the generalizability of it.
That's a pretty useful improvement. So there were a few other questions. Sophie Valk asks, how far does the assay correction affect effect sizes? Is that something you've sort of systematically looked at?
That's a Good question. I mean, so if you look in the paper, which is now in press in the Gradients special issue of Neuroimage, we go into how it basically broadens the null distribution, and therefore is able to give you, you know, a distribution over what your actual null hypothesis is, which is that there's something special about this topography relative to other topographies, rather than there's something special about this map relative to white noise, which is what you do if you have a kind of randomized, you know, scrambled map essentially. And so that also comes into play. I don't know if this quite came through in the talk with the gene set enrichment analysis, right? So often the p-values that you get out of a standard GSEA analysis is that a gene set, a given ontological category, is enriched for this gene relative to other genes. But the actual hypothesis when we do these kind of map GSA analyses in neuroimaging is that we're trying to make some inference or claim about the specific topography of that map of interest. And so what we found is that any spatially autocorrelated, in this case, cortical map, ends up having preferential enrichment in certain categories. And so you can't really make a claim about the specific topography of the map of interest. So to test the null hypothesis you actually care about, which is about topography, you need to compare not your enriched genes to random genes, but your map to random spatially autocorrelated surrogate maps.
So I guess that also kind of taps into the next question by Alexandros Goulas, asking whether like the associations that you're kind of using for this spatial autocorrelation, whether they automatically then render those like non-interesting. So basically, because you're kind of basing your null models on these spatial autocorrelations.
Again, it's not that it's not interesting, but it you know, the test that you do needs to be specific for your question, right? What is your null hypothesis? And if your null hypothesis is there's something preferential about my map relative to white noise, you know, that you can do that in a standard test, but people might not find that you're really answering the question of interest, right? But if you actually want to make a claim about this specific topography and this specific alignment, then you need to do the comparison to other maps which have the basic features. In this case, I would say spatial autocorrelation is one of the most prominent ones to control for. But then, you know, then you're able to specifically test about the specific topography of your map of interest, which is where I think most papers are trying to, you know, make claims.
I think that's probably all the time we have for questions, since we're already running a little bit behind time. So I'm just going to hand it over to Casey.
Some of these later as well. So next up, we're going to have Sophie Valk, who has just started a group in Leipzig, the Cognitive Neurogenetics group. And while they set up Sophie's talk, one thing we asked some of our speakers was what their favorite gradients papers were. And I found out that Sophie has a crush on the cerebellum. And so she really likes the cerebellar gradients paper coming out from Xavier Guel, which I agree they're papers as well. So maybe will you do something on the cerebellum soon, Sophie?
Let me unmute myself. God knows, I have a crush. Sometimes you cannot explain the reason why. But I came upon the cerebellum in a post hoc test from a different paper where it was not the focus. So now I'm a bit intrigued.
Mm-hmm.
But I hope the crush will pass because I have more expertise on the cortex. So.
Well, crushes do pass. That's the beauty of them.
That's my hope. It's a summer love. So.
Yeah. Okay, let's see Sophie's talk.
Hello, I'm Sophie. I'll tell you something about the shape of brain structure, the genetic and phylogenetic axis of microscale organization of cortical thickness. Cortical thickness is measured in the T1 image, MP range or MP2 range, where you measure the thickness from the gray white matter surface to the pio surface. And what you do is you have this vertex setup, this tessellation of the surfaces, and you measure the distance between corresponding vertex points in both surfaces. So with that, you have cortical thickness of the whole surface. And what you can do with cortical thickness is that you can measure structural covariance, which is a population-based measure of the covariance of seed thickness and target thickness. So for example, you take the thickness across a population of a seed region here in the anterior insula and a target region here in the sensory motor cortex, and you see if both have a correlation, which in this case they do. So using this method, you can do this for the whole cortex, where you can get a cortex-wide covariance matrix. And what you see is that regions that are relatively close to each other usually show a high correlation, and also regions with contralateral homologs show a high correlation. That's why these lines are here. Search covariance can be largely explained by genetic factors. So if regions have a high search covariance, it's likely the case because they have shared genetic factors. So already in 2008, using a twin sample, it has been shown that these also form certain communities which are hierarchically organized. Second, social covariance relates to maturational coupling. So regions that show the social covariance also mature in similar ways during development. A different line of research, and we are in the gradient workshop, is gradients, which studies the large-scale organization of brain structure and function. And in a very nice paper, Daniel could show that there is this large-scale organization gradient in the human brain at rest, which goes from unimodal regions to more heteromodal association cortices here in the default mode network. And this organizational patterns corresponds also with theories of, for example, Marcel Mesulam, stating that there's this organization pattern going from more unimodal regions to higher order regions that relate to more internal processes. And indeed, like looking at the neurosynth co-activation of meta-analytic atlases, he could indeed show that in the lower percentiles along the gradient, they mostly correspond to motor processes, pain, action, eye movement, visual perception, whereas the higher ends of the gradient seem to relate more to abstract thoughts, such as social cognition, emotion, verbal semantics, and autobiographical memory. So it seems that the organization of the cortex tells us also something about the organization of cognition. So to sum up, macroscale patterns in cortical organization relate to human cognition, and cortical thickness covariance reflects shared maturational and genetic processes and is organized into multiple communities. But why? The reason for their particular spatial relationship remains unclear. So in our current study, we sought to directly examine the genetic origin of the spatial organization of macroscale cortical features. Let's go. So we used the nonlinear dimension reduction approach based on the BrainSpace toolbox of Rainer Vosterwaan, which is a great toolbox to measure gradients, and it's easy for MATLAB and Python. I used it in MATLAB, but Python is definitely also great. So what I did is I had a covariance matrix. I performed a normalized angle procedure to normalize my data. And then I performed diffusion map embedding to get the gradient ordered embedding of each region based on this structural covariance pattern, and later also based on this genetic correlation pattern. So what I found is two gradients. One goes from posterior regions, which are largely also unimodal regions, to frontal regions, and the other one from inferior regions to superior regions. Okay, nice, but nice colors, but what does it mean? So first, I also looked at how it corresponded to this organization pattern that Daniel also showed from unimodal to default mode network. And indeed, this first gradient seemed to have some correspondence to this functional organization, whereas the second one did not really do so. So yeah, nice. I've shown this is in the ACP sample, this patterning, but then I wondered, is it actually robust? So for this, I looked at the ENKI sample and I did the same procedure. I took the covariance matrix and I evaluated what are the two major organizational axes. And again, what I found was this posterior to anterior patterning on the one hand and inferior to superior patterning on the other. Then I also tested whether it mattered if I use FreeServer 6.0 or CVIT, but always there were largely these two patterning going on from posterior to frontal regions and from inferior to superior regions, or from, no, that was how it was. It was actually not, it was always the same. And also using different parcellation schemes, I also found like the Seacon, Glasser, Schaefer all largely gave this similar effect going from posterior to frontal regions on the one hand and inferior to superior regions on the other. Like it's important to know there are small differences between these patterns, but overall they're kind of comparable. So next, I used advantage of the twin-based setup of the ATP young adult sample, and This sample includes monozygotic twins, dizygotic twins, and also unrelated individuals, which made it possible to further deconstruct this covariance matrix into genetic correlation and environmental correlation by looking at the genetic similarity of each individual and how this relates to the correlation. And indeed, as also other people have shown, we found a high relationship between structure covariance and genetic correlation, and not so much to environmental correlation, which is also something that has been mostly attributed to noise, but part of it is also likely other factors that are all put in this environmental correlation aspect of the correlation. So moving forward, I also looked at how it aligned with functional communities, and what you see is there's a high genetic correlation, sort of high, within a functional community, but not so strong across functional communities, and a very weak but kind of similar pattern was observed in environmental correlation. So it seems that genetic correlation is also organized, and then I performed a gradient analysis to see what is the spatial organization of genetic correlation, and I found again these two patterns. So on the one hand, this posterior to frontal patterning, and the other one inferior to superior patterning. And indeed, this first gradient again corresponded to functional organization as described by Daniel, but the second gradient did not so much, or did not at all actually. So first I could show, okay, these spatial patterns in structural covariance are likely due to genetic factors because there's such a high correspondence between the structural covariance gradients and the genetic correlation gradients. However, what about phylogeny? Is there any, is it evolutionary conserved? So for this, I looked at macaque monkeys, and I took advantage of the PRIME dataset, which is an open dataset with non-human primate data, and with cooperation also with Ting2 from New York, we created a covariance matrix of thickness in macaques in a similar way as in humans, and we performed a gradient analysis. And what I found was two main gradients, one going from temporal regions to sensory motor posterior cingulate regions, and the other one going from sensory motor regions to frontal regions. Well, nice. I colored them a bit like suspiciously similar to the human gradients, but are they actually comparable to the human gradients? So for this, I used a really nice approach which Ting also developed, and I transformed the human gradient to the macaque space. And using this transformed gradients, I was able to directly compare the human and the macaque gradient. And what I found is that the human principal gradient corresponded roughly to the macaque secondary gradient. So you see here, there's a positive correlation between the macaque G2 and human G1, whereas between macaque G2 and human G2, there is a negative relationship, but this was not statistically significant. On the other hand, the human secondary gradient related to the macaque principal gradient. So cool, the gradient seems phylogenetically conserved, which is interesting, I guess. So using the gradient methods, we kind of were able to move a little bit forward and understand like what is the genetic basis of covariance and why is it spatially organized in the way it is. So like this posterior to anterior patterning, it relates to a functional hierarchy, and this inferior to superior patterning, like, well, I couldn't answer it. I found it in humans and macaques. It was also there in genetic correlation, but what it was still like unclear. So for this, then we looked at the theory of dual origin, which is a seminal theory stating that cortical development stems from two origins. One is in the archicortex, the hippocampus, roughly, and it follows these arrows. And the other one is in the paleocortex, which is also the piriform cortex, and it follows these arrows roughly. So the dual origin, it relates to cortical differentiation. So it goes from low, medium to high cortical differentiation from both origins, so to say. So probing this model, I used the geodesic distance from both the archicortex and the paleocortex distance, and I wanted to see if this theoretical model would also reflect the large-scale organization I found in structural covariance. And indeed, you see when you order covariance in bins, you see that there's a high covariance at similar distance from the archicortex and also the paleocortex. Then I also looked at my gradients, and what I found is that the gradient 2 had a negative relationship to archicortex distance, but a positive relationship to paleocortex distance, possibly showing that this gradient might reflect this dual patterning, whereas the first gradient, I did not so much relate to it at all. So it's kind of a nice dissociation as well. And we could also find similar patterns using a similar approach in macaque monkeys, where we found this gradient 1, which corresponds to gradient 2 in humans, showed this inverse relationship to the dual origin distance, whereas the second gradient did not so much. So the take home is that this covariance is organized along evolutionary and functional axis. The posterior-anterior patterning relates to its functional hierarchy, whereas this inferior-superior patterning relates to the dual origin. And another take home is that I have a big thanks to open neuroimaging data, because I used the PRIME dataset, I used the ACP dataset, and ENKI. All these datasets are not scanned by me, but I was just able to take advantage of all this great open neuroimaging. So thank you so much. An important point, like, what about distance? Because as some of you might know, distance is like an important organization principle in social covariance. And regions that are super close to each other, they show often a high covariance, whereas regions that are distant to each other don't show such a high covariance. And indeed, if you take the gradient of GODs, the distance, you see almost this highly similar pattern. So like maybe what I just showed was just pure like geometry and distance. And the same is also true for macaques, actually. So humans and macaques, we see this, and like first I was like, oh no, maybe it's not so meaningful after all. But then we regressed out distance in our covariance matrix, and what we found is these two patterns. And it's important to know that this first gradient, it corresponded both to G1 and G2, but what is important, we still find this dissociation, that gradient 2 shows a statistically significant association with Daniel's organization, whereas only the first gradient, so the gradient got reversed when correcting from distance, showed that relationship to the dual origin. Which is kind of nice, is that still if you remove the distance organization, still this functionally hierarchy and this dual origin are still present in social covariance. And the same was the case for macaques, and even a little bit clearer maybe, where you see a clear relationship to the archicortex, paleocortex distance in the first gradient, but not so much in the second. And you see also a clear correspondence between gradient 1 and gradient 2 and the non-corrected gradient 1 and gradient 2. So this is, I hope, a happy end to a very nice project, and I was super honored to work with great people. Simon Eickhoff, of course, for supporting me during my postdoc. Ting, Daniel, Georgette, Casey, Alexandros, Peter, Jonathan, Thomas, Boris, like, thank you all so much for your support and your creative insights and your help with this amazing project. And thank you for listening to me.
Thanks, Sophie. I have a question to start us off, actually. So because the diffusion map embedding that we use, it does create orthogonal eigenvectors. Based on that, would you then infer that the functional hierarchy and the dual origin are also orthogonal?
Great question. I think yes and no, because like the question is also like how like I've done some follow-up projects also on these two dimensions, and I guess in a way there are some ups and downsides about the dual origin either. And if you take the absolute value of the dual origin, you get kind of this functional expansion. So most expansion occurs at the like meeting points of the dual origin. Although I also spoke with Daniel, and like it doesn't quite fit yet. So I'm still banging my head against that wall to break it. So like in the end, all gradients are connected. Like it is a dynamic space that is like has a multiple. And so in that sense, I think they're not completely interdependent.
Yeah, I'm trying to disentangle what that interaction is and whether they are like intersecting, how they converge and how they differ.
Yeah, and I guess also things work will later also show like how the evolutionary expansion occurs, and this is also like it matches with the functional gradient, but not 100%. And then looking at the gradient of task-based co-activation, you see a little bit more dual origin in there because it places the dorsal attention network and the default mode network a little bit further apart than in the traditional functional gradient. So I guess to know how all these dimensions fit together is still really an open question, and how to look at this interdependency. So yeah, yes, and like I'm super intrigued by it, but.
I mean, have you looked at the relationship?
Oh, Johnny, you go.
Have you looked at the relationship with distance, the way that Daniel calculated it? I mean, the only reason I'm saying that is because it feels like the modality must make a difference, I think, in the maps anyway. So as soon as you go into a functional space, there must be like, it must combine things like neuromodulation and stuff like that in the way the maps are formed. But it feels like the mapping between the geodesic distance couldn't have that problem, because that basically is a property of the structure.
Yeah, so yes, I corrected for distance in my covariance thing, and I still showed the two origins, but
I didn't mean correcting for it, because the reviewer who kept asking for that, I think he's misunderstanding everything. I just meant that, you know, so in Daniel's paper, there's the functional modes, and then they map onto the distance mode, basically.
Yes.
Right? And I was just wondering whether or not, like, you know, do you find when you apply these analyses to the structure itself, right? So that removes the function from the problem. Do you see a mapping with like a distance map, you know, the way that Daniel calculated it?
Yes and no, but not in the same way as Daniel saw it. But I do see, if I look at connectivity distance, because you take the top 10%, it is a bit different because like covariance is inherently local. And functional connectivity doesn't have this distance bias. So you can also get this long-range connectivity patterns a little bit better. And I also work with microstructure profile covariance a little bit. And also I looked at the covariance. So it is also a question, like we talked also a bit about it over email, of signal to noise, right? And every method has its own strengths and weaknesses. So I guess functional connectivity and task of resting state can quite well get also faraway regions to some extent, but the question is also like, what does the variability mean? But these covariance metrics, they have a little bit of a bias that they're super good close by, but the further apart, it gets more and more challenging to get it right. I guess also because it becomes more noisy and, but yeah, that's also with like any distance question, like what is the signal, what is the noise? And also with this spatial autocorrelation, like it's, in some ways, there is also signal in it, right? And in some ways, it is not relevant to the question. So to disentangle all these different routes of noise and information and lack of information. But yeah, with Daniel, I find it super elegant and fascinating, like also this distance from unimodal regions. And it's definitely something that keeps me up at night.
I don't know if that's good or not.
With that, I might just pass to Richard to introduce our next speaker.
Yes.
Thanks.
Well, great. So it's my pleasure to introduce Jake Vogel, who's going to talk to us a little bit about how molecular gradients coordinate spatial organization. I have to say, I was quite surprised to learn that Jake's not already a PI, because I've seen a couple of his papers and I've seen like what an amazing output he's already had and what an amazing impact he's already had on sort of mapping, imaging, and genetics. And I only learned this week that he only passed his PhD last week. So I'm very glad that he was able to like take some time off celebrations and join us for this workshop. And with that, just let's dive straight into his talk.
So I want to start by thanking the organizers for including me in this riveting day of talks. The program is filled with great speakers whose work I've been following for some time, so it's an honor to be included alongside them. So I'm going to talk about two studies that explore the relationship between gene expression gradients and the functional organization of the brain. So I'm going to take both a local view in the hippocampus as well as a more global view across the whole brain. So I certainly don't need to introduce this topic too much, but we all know that the brain can be characterized in terms of regions representing areas of shared function or architecture, but also gradient-like representations where gradation and function is organized systematically across specific linear or nonlinear axes. So regions and gradients coexist and interact hierarchically to influence overall brain functional organization. So the origins of this organizational structure might come from patterns of gene expression during development. I'm showing two examples here, one from the developing spinal cord on top, and also an example from the cortex at the bottom. But in both cases, broad sort of gradient-like expression of a few genes help to coordinate and recruit the expression of other genes in a more discontinuous or sharply bordered pattern. And this leads to brain arealization. So a similar theme, this is pretty similar to the one I touched on earlier, except we're seeing it here with actual gene expression. And we do know of some genes in the human brain that coordinate this organization, but it's generally pretty difficult to study this in humans for obvious reasons. But that's changed somewhat with the introduction of the Allen Human Brain Atlas, which I'm sure most of you know quite well. The data set features 6 brains from which 3,700 tissue samples have been extracted with really excellent brain coverage. And each tissue sample has undergone microarray gene expression analysis of 59,000 probes targeting 20,000 genes. And importantly for our purposes here, each sample also includes stereotaxic coordinates expressing the approximate location of the extracted tissue. So this allows for hypotheses to be tested concerning how gene expression is associated with or influences spatial organization of different brain structures. So I'm going to talk about 2 studies from our lab that takes advantage of this information. And a good place to start would be the hippocampus. So it's a relatively small structure, but it's one where we can see a lot of these ideas being represented. So, most of us are aware that the hippocampus can be parcellated into several subfields. And these are kind of, the regions of the hippocampus, if you will. And, aside from being distinct in their cytoarchitecture and their connectivity, the subfields also show, a fairly divergent pattern of gene expression that lets you differentiate them. But gradients can be observed in the hippocampus as well. And in particular, there's well-documented evidence of behavioral domain specificity and connectivity patterns varying systematically along the longitudinal or the anterior posterior axis of the hippocampus. And this has been demonstrated quite elegantly in humans by several labs. However, the same longitudinal organization has also been shown in mice and other rodents, where different investigators have studied how transcriptomic patterns influence this functional organization, finding contributions from both gradient-like expression as well as sort of regional subfield expression. But similar studies were lacking in humans, so we set out to map a transcriptomic gradient mirroring the functional gradient along the longitudinal axis of the hippocampus in humans. So we first identified we wanted to sort of deal with the curvature of the hippocampus. So we identified a hippocampus skeleton, and we also identified 170 tissue samples from the Allen Brain Atlas that were in the hippocampus. And we found the closest skeleton coordinate for each one of these samples. So the goal was to have a single coordinate indicating where along the longitudinal axis of the hippocampus the sample fell. So we trained a machine learning algorithm to predict this location, so sort of where the sample lies along this anterior posterior axis using just the transcriptomic information. So using cross-validation, we found that our model could predict the location of the sample along the longitudinal axis of the hippocampus with pretty high accuracy and pretty low error using just this gene expression information. And this perhaps indicates the presence of a consistent molecular gradient underlying the aforementioned functional specificity along this axis. And using a leave one subfield out framework, we importantly found that these results were actually fairly consistent across and therefore probably orthogonal to the hippocampal subfields. And similarly, we found a leave one donor out analysis found pretty consistent results across the different donors. So To ensure these results were not limited just to the Allen Brain Atlas, we took advantage of a subset of the BrainSpan dataset, which includes RNA-seq data from laser microdissected samples from the brains of 4 prenatal human donors. And there were no coordinates, but we could use the precise anatomical labels to differentiate samples dissected from the posterior versus the anterior hippocampus. And so by applying our model to these data, we found we were able to discriminate the anterior from posterior hippocampus quite well. And that indicates not only that this model generalizes outside of the Allen Brain Atlas, but also that this genomic gradient appears to be active already during fetal development. So next, we were interested in how this gene expression gradient might influence relationships between the hippocampus and the rest of the brain. So we took non-hippocampus samples and we fed them to our model. We basically asked, I know you're not in the hippocampus, but if you were, based on your gene expression pattern, where along the longitudinal axis would you fall? And we kind of used this information to create what we call haggis, which is an index where higher values represent greater transcriptomic similarity to the anterior hippocampus, and lower values mean greater similarity to the posterior hippocampus. And when we looked across the whole brain, we saw this interesting pattern where brainstem and more anterior-ventral portions of the brain appeared to have a transcriptomic signature that was more similar to the anterior hippocampus, while the more posterior dorsal and brainstem and cerebellar sites were more similar to the posterior hippocampus. And we found that this haggis gradient, which is shown smoothed here at the top, was informative with regard to several cortical hippocampal relationships of interest. For example, we found a region's connectivity or structural covariance to different parts of the hippocampus were correlated with how similar its transcriptomic signature was to the hippocampus. And similarly, we found that this signature discriminated regions more vulnerable to Alzheimer's disease from those regions more vulnerable to frontotemporal dementia. So pretty interesting stuff. And we also performed a cognitive meta-analysis using Neurosynth and identified brain networks that not only shared similar expression of this hippocampal gradient, genomic gradient, but also which were involved in disparate cognitive or behavioral tasks. And these results corroborated really our expectations with regard to domain specificity of the different sort of poles of the hippocampus. So we started in the hippocampus, but we sort of ended up with this large gradient across the brain that seemed to influence or relate to 2 dissociated functional brain systems. And it got us thinking whether this could be considered the other way around, whether this hippocampal gradient might just be the local expression of a common brain-wide gradient. So that sort of influenced our thinking in the next study, where we zoomed out from the hippocampus and started looking across the whole brain. So in this study, we took a pretty similar approach, but instead of looking at just the hippocampus, we looked at tissue samples across the whole brain. And instead of constraining space to a single dimension, we actually looked across all 3 spatial dimensions. So for this study, we used cross-decomposition. We passed the gene expression information for a given sample to the X matrix and 3D spatial coordinates to the Y matrix. And we were hoping that the covariance of these factors might identify genomic gradients in the adult human brain. So we split our data into a training and test set. And in the training set, we used cross-validation to identify that partial least squares regression with the maximum number of components was the best model. So we also saw that all 3 of the components that we extracted explained variance in the spatial data far greater than expected by chance. And in our left out test set, we used the PLS model to predict the 3-dimensional spatial location of these unseen samples based just on the transcriptomic information. And here you can see the predicted values of the Y, Z, and X coordinates from top to bottom for each sample. And we found the model predicted location very well in this unseen data along the rostrocaudal and dorsal-ventral axes in particular, and maybe a bit less well along the medial lateral axis at the bottom. And to kind of visualize this, here we plot the Y and Z coordinates of each sample in the Allen Brain Atlas, and you can see the different brain regions are colored differently. And here's the predicted location of each of those samples with the same coloration. So the predicted version doesn't really look like a brain, but the spatial relationship between the major substructures is more or less preserved. And here we're just visualizing the model error, where samples in red had the worst prediction. And you can see the model seemed to perform the worst in parietal and prefrontal regions. But we were satisfied enough with this to move forward with characterizing the spatial and genomic qualities of these PLS covariates. So here's the first component. Okay, so the genomic expression of this component is visualized on the bottom, and a covariant linear gradient through space is shown on top. And we're seeing a transcriptomic signature that has sort of a ventral to dorsal emanation, and it seems to separate on the genomic side the cortex from subcortical structures. But we felt that perhaps a more elegant description of this gradient might be that the component differentiated brain regions based on their rostrocaudal position in the developing human brain. So as you can see here, component 1 expression is lowest in regions that originate in the telencephalon, and they increase as one moves caudally along the neural tube to regions originating in the met and myelencephalon. So once again, we wanted to replicate this data from another source, and we once again turned to the BrainSpan data set. So BrainSpan has great cortical coverage as well, but only has a few cerebellar samples outside of that. So here I'm showing how cortical and cerebellar samples are strongly dissociated by component 1 in the Allen Brain Atlas data set. And we replicated the same finding in BrainSpan with just the cerebellar and cortical samples. And furthermore, the BrainSpan samples were extracted from donors across the lifespan, from sort of prenatal development all the way through adulthood. And we wanted to visualize how this relationship with component 1 evolves along the course of development. So here you can see that the samples were arranged from earliest age at 8 post-conception weeks, all the way through to oldest age, which is 40 years. And we found that component 1 began to differentiate these structures, already during the fetal period of development and plateaued in early childhood. So we also defined a second component that was characterized by this sort of posterior to anterior radiation. And it really seems very reminiscent of the hippocampus-based gradient that we found in the first study. But based on our conjecture from component 1, we wondered if this gradient might be important for regulating instead the dorsal ventral axis of the developing brain. And in each segment of the developing brain, we separated regions based on whether they originated in the dorsal or ventral part, and found that component 2 expression was consistently higher in the dorsally originating regions. And in the telencephalon, we found a specific pattern of expression that was lowest in the subcortex and increased as one moved from the frontal lobe and a posterior direction along the cortex. So once again, we wanted to replicate this in BrainSpan. And for component 2, recall that the expression in the cortex, which is where we had most of the coverage in BrainSpan, differentiated limbic from anterior from posterior cortical structures. So as such, we calculated the mean component 2 expression in several regions in the Allen Brain Atlas and correlated this with the mean component 2 expression of the same regions in BrainSpan. And we found a pretty remarkable correlation between these two data sets shown here. And this, not only indicates the generalizability of component 2, but again, we can see that component 2 expression began differentiating structures prenatally. And interestingly, in this case, though, the process seemed to continue through into adulthood. So it might be a little bit more dynamic. So finally, the last thing we did was, we were interested in whether these whole brain gradients might intersect and interact to promote cortical arealization. So we took the spatial gradients of the first 2 components and the third component, which I didn't have time to discuss here, and we just projected them across the brain to see where they overlapped. Pretty simple. So here I'm showing regions that shared concentrations of these different gradients. And, this is fairly speculative exercise, but if one squints, maybe you can make out some recognizable anatomical divisions of the cortex, see the parietal lobe or occipital lobe, and so forth. And so this is pretty interesting to us. And if you repeat the same exercise using instead the genomic components of the PLS covariates, which might be more relevant, this time the gradients define more of a sensory fugal axis. So you can see the primary sensory structures are differentiated from the sensory structures, the sensory support structures, which were then differentiated from heteromodal cortex and limbic structures. So all in all, in these 2 studies, we identified patterns of gene expression that occurred systematically along spatial gradients in the brain, both locally and more globally. The components were reproducible across and within cohorts, and they appear to emerge prenatally. So while it requires further follow-up work, we are interested in understanding, testing whether and how these gradients may be involved in cortical arealization. So the first study has been published recently in Nature Communications if you want more information. That also includes all the code that we use to do all the analyses and make all the plots. And if you'd like to learn more about the second study, it'll be presented at OHBM on June 30th. at 7 p.m. Eastern time in the US, I think around midnight UK time, or you could just find me during the poster sessions. So with that, I'd like to thank my co-authors, our funding bodies, particularly the many amazing data sets and tools that made this research possible, and thank you for your attention.
Well, thanks, Jake, for a really amazing and like a very comprehensive talk. So it's open to questions. If people want questions, please like leave them in the chat. I saw Jake's already like been answering a couple of them. I'm not sure if Jake, do you want to maybe expand on any of the answers that you've already given?
Yeah, sure. So I think John had asked earlier, you know, let's see, what did he ask? We get, that's my answer. Sorry, the simulated jet lag is real for me. Okay, does the prenatal data suggest that the molecular gradient strengthens over development, or the pattern is strongly set even prenatally? Yeah, that's something that we're really trying to get at, especially with, we didn't look at it as much in the first analysis with the hippocampus, but we're trying to get at it more with the second one, which is basically, you know, when did these gradients become relevant? And it's kind of interesting to look prenatally because it's, you know, things are happening extremely dynamically during that time, both in terms of what's happening to the molecular milieu, but also literally how the brain is moving around in space, literally as it's evolving. So we're kind of trying to get at, I mean, what the data shows so far is that there is some of the gradients might not be there at the very sort of beginning of when we're measuring, which is like, I think post-conception week 10, but it emerges pretty rapidly during development and sort of continues to emerge until, you know, until basically infancy, at which point it kind of plateaus. So it seems like it's something that is somewhat dynamic early on and then mostly plateaus, but we're really, sorry, go ahead.
Maybe you've touched upon this in your talk already a little bit and I just missed it, but do you see like any sort, like if you think of like the canonical gradients that have sort of been presented so far, like the first 3 gradients, if you have to like pick a point during development where you see that clearly emerging as 3 separate, is there like a point in development where you can pinpoint that sort of separation a little bit, or do you expect like maybe like gradient 1 sort of diverges first and then like the sort of the boundary between gradient 2 and 3 emerge later? Is there any sort of way of backtracking that?
Yeah, so are you referring to sort of the canonical Margulies functional gradients?
Yes, yeah, essentially.
Yeah, so I mean, I can only speculate because we didn't sort of look at that directly here. Our sort of third component was one that actually did look a lot like the principal, you know, gradient, although it's not one that we were able to replicate in BrainSpan, so we didn't follow it sort of over development. But you know, it is a bit hard to say because the 2 gradients had kind of, in our study at least, had kind of different trajectories over development. The one that was sort of more anterior posterior, which I guess is maybe a bit more relevant for cortical organization, maybe similar to something that Sophie had showed just previously, that did seem to kind of continue, based on the limited data we have, kind of continue to differentiate regions more and more through into adulthood. So I mean, it's hard to say based on the data that we have. It's definitely something that we have to replicate and look further into. But I think that, you know, if you could map the genomic information onto these sort of connectopic gradients, which, you know, I think you could, you can use the same kind of rubric that we did to track how it changes along these samples in BrainSpan. I think that'd be a really interesting thing to look at.
Thoughts for future projects, perhaps, or maybe someone in this chat's already working on it. Were there any other questions? Otherwise, I think we're just going to move to the last speaker, who Casey's going to introduce.
Yeah, our last speaker is Ting Su. She's working at the Childmind Institute in New York at the moment. And so, Sasha, you can take away and start with her talk if you like.
Hello, I'm Ting Xu from Childmind Institute. It's a great pleasure to have this opportunity to share the work at this gradient workshop. I'm going to present a cross-species functional alignments based on the gradient and to show how it can review the evolutionary hierarchy within the connectome.
The cross-species comparison is very important for understanding the human brain organization and the brain evolution. For example, previous studies have shown that evolutionary cortical expansion from macaque to human has very similar pattern compared to the childhood cortical expansion. It also has very similar pattern with the inter-individual variation and the long-distance connectivity distribution in humans. In response, it is essential to establish the alignment between species for such comparison. And this can also facilitate the translational efforts in animal models. The benchmark alignment in last decades was proposed by David Van Essen. This approach made use of common recognized anatomical landmarks to register cortical surface from one species to another. The more recent efforts from Roger Ma's group made use of white matter tracks and myelination to align non-human primates to humans. One recent effort started to use functional data while human and macaque are both watching the same movie to align them together by comparing the neural activity during watching movie. But what else of brain function is comparable for us to do the alignments? So the answer might be gradients. If we can identify comparable gradients between macaque and human, then we can align them together. And this seems to be possible based on Daniel Marcus' gradient work, showing that human and macaque brain have similar hierarchy gradients along the surface. So here, I use two public available datasets to do the analysis. For human, it's Human Connectome projects, and for macaque monkey, it's Primate Data Exchange Consortium. Instead of using diffusion embedding for each species to match the gradient afterwards, here we propose a joint embedding approach, which can extract the matched gradients in human and macaque simultaneously. So how do we do that? We start with this gradient, with these anatomy landmarks that may be established in the Van Essen and Roger Ma's work. And then we first calculate the vertex to landmark functional connectivity within species, and use this vertex to landmark connectivity profile to get the human connector of human macaque similarity matrix. Then we can build a joint similarity matrix to place the within species similarity on the diagonal part and the between species similarity on the off diagonal part. We can perform the diffusion embedding algorithm on this joint similarity matrix to extract the components. We can also call the components gradient here. And the first half of the gradients were matched with the human vertices, and second half of the gradient matched with the monkey vertices. Then we can use each gradient or these components as one dimension to build a high dimensional space. So here is the first dimension. Each node in human and macaque can be projected in this high dimensional space. And each node also corresponds to each of the cortical vertices on the human and macaque surface. As you can see here, they align quite well in high dimensional space and being on the surface. This is the second dimension. Highlights the gradient from sensory motor regions to high order associated cortex. The third dimension. Now we show how it can be aligned in this space. In this way, we can link human brain and macaque brain together. For example, we map the glassy parcellation from human to macaque brain. And finally, we can simulate the evolution of surface expansion from macaque to human. One thing I didn't really include in the animation is the surface matching process. Let's record this gradients for a second. Once we put the gradient on the surface, we can actually align the gradients, use this gradient as a cortical feature to align them in MSM, the multimodal surface matching. So here we show that alignments can align human mind map, which is T1 divided by T2, and map into the monkey surface and compare to the real T1 divided by T2 calculated in the monkey space. So we see that these two mind map is quite comparable. So to demonstrate the alignment works. Based on this functional cross-species alignments, we can also map the human parcellation into the macaque surface, and another way around from the macaque parcellation map back to the human surface. We can also map functional connectivity between human and macaque. Here is an example that we place the seed in human deformer network, the dots, the black dot here, and to show the corresponding connectivity, how it looks like in the macaque brain. We can then measure the local maximum cross-species similarity based on the gradients. We just name it as functional connectivity homology index. So this index represents the likelihood that brain function gradients in one species can be represented in another species. As you can see here, this index showing that very high cross-species similarity sitting in the primary areas. For example, the V1, MT, the primary auditory regions, the FFA regions, even though the FFA regions is not included in our landmark sets. And one thing we noticed that the TPJ, temporal parietal junction, has 0 index, which indicates that we cannot even find the similarity in macaque, similarity function gradient in macaque as compared to human. This is consistent with literature, as many studies suggest that human TPJ might not exist in macaque. At network level, we find the homology index follows hierarchy, that primary networks show high similarity, while the high order social cortex, like frontal parietal and deformer network, showing low similarity. We further look into more local regions and show that functional homology also follows the hierarchy in the local regions as well. So for example, the early visual pathway, the circular radiation patterns in the MT regions, the ventral visual pathway, and the dorsal to ventral topology at this symmetry sensory regions. For the subsystem in frontal parietal and attention networks, the functional homology also shows a hierarchy as well. For example, the frontal parietal subnetwork A, which is more relevant in mentalizing and emotion in the literature, showing the low homology index here. And the attention subnetwork A, which is highly connected to hippocampus compared to network B in the literature, also shows low homology index here. In deformer network, we looked into 3 subsystems. the core deformed network, which are more associated with self-reference in the literature, are showing a lowest similarity of homology score here, and followed by this dorsal medial subsystem, which is more relevant to mentalizing theory of minds. The highest homology score found in deformed network is this medial temporal system, which is more relevant to our memory system. We also correlate the homology score with the importance rank of deformed network subregions based on a recent study. So we find a significant negative correlation between importance of default subregions and this homology index. So this indicates that the most important subregions in deformed network has the lowest cross-species similarity. In other words, the most important subregions in deformed network in human might have developed the latest in evolution and has the recent evolutionary adaptation. So here we show the cross-species similarity map seated in macaque brain and how it looks like as compared to human deformed network. Surprisingly, the similarity pattern of a few deformed network regions in macaque doesn't really look like the typical deformed network in human, but more like a frontoparietal and attention network. This suggests that macaque may have deformed network, but it is still under development and it's not at the same hierarchy level as compared to a human deformed network. In particular for the dorsolateral frontal lobe, the posterior middle cortex like PCC and brachiornis, the TPJ area, which is the parietal gyrus here. We also link the homology index to the cognition components and find a negative relation here. So the high level cognition components is more likely to locate it in the region that has a low level cross-species similarity. Finally, we demonstrate the evolutionary deformation from macaque to human. For example, the macaque V1 is sitting on the lateral occipital lobe, but in human, it's all in the medial occipital lobe, which means in the evolution, maybe the V1 region has been pushed and squeezed from lateral into the medial and has the higher deformation here. And the expansion from the frontal lobe in human has also pushed the parietal backwards in general. And such expansion can, such surface expansion also follows the hierarchy between networks as well. So taken together, we demonstrate the joint embedding approach to provide a solution for cross-species alignments. We developed the functional connectivity homology index to quantify the cross-species similarity. And this index varies between and within networks in hierarchy manner, which reflects the gradient of evolutionary change from unimodal subsystem and the transmodal system. In addition, our finding provides important view on how the deformed network may have emerged in humans. The deformed network as epic of cognitive hierarchy is a relatively recent evolutionary adaptation. I'd like to share the credits with Carl Snelling from Viagland's lab. And many thanks to Mike, Giag, Daniel, Johnny, all my colleagues and collaborators. I also would like to express my special thanks to Daniel Maglis. He is my inspiration for many gradient work. And thanks to HCP Data and all the lab that generously share their data on the Prime DE. And thank Boris and all the organizers again for this workshop. And thank you for your attention.
Thank you so much, Ting, for that. Are you online with us? There you are. Hi.
Yes. Hi.
So cool. Let's start with a couple of questions that will come in through the chat. So it's one question about how widely can this extend across different other types of species, and maybe you could comment on the different types of challenges you'd face when going across more different species than just macaque and human, for example.
Yeah, that's a great question. I actually tried to map the macaque and to link to the rodents, but it's really difficult to find the comparable gradients between between the rodent mice data to the macaque. I think it might be possible if we have like a small animal sitting in between the mice and macaque, for example, the marmoset or the lemur monkey, that will make it possible.
And would you put all of those into the same model, or would you do it in more of a stepwise fashion?
I would say it would be like stepwise fashion, like, for example, in Roger Ma's work, using the mapping map T1 divided by T2. It's difficult to map from macaque to human, but using chimpanzee as a middle point, then you're able to map macaque to chimpanzee and chimpanzee to human, and finally establish the alignment.
Very cool. And then there's another question, does connectivity homology index correct for the region of interest size, coming from Ruby?
Sorry?
So that was, does functional connectivity homology index correct for the region of interest size?
Sorry, it just, there's some noise outside.
Oh, it's so your functional connectivity homology index, do you correct that for the region of interest size?
No, not really. I just search around, so for each vertex in the human, and we find the corresponding vertex in macaque based on the MSF, which is topology constraint alignments, and the search around on the macaque surface in less than 12 millimeters sphere, and finds the maximum similarity, which represents in the local region what is the maximum similarity you can find cross species.
Yeah, there we go. I think that answers that question. And then there's a question from Boris. So can you extend the joint embedding approaches to incorporate further features, for example, microstructural similarity? And do you see any benefits there?
Yes, definitely there's something I would like to try, because I got a lot of challenge comments and saying functional data is not really stable, for example, to capture the features, and adding more features, for example, the mapping map or microstructure, that would be helpful to make it more stable and more representative.
Very cool, thank you. So I think with that, we might invite all the speakers from this session back on screen. So if Jake and John are still around, do you want to join us again? I think we'll just have like a few more minutes for some kind of broader questions to everyone. So I have one that I kind of want to be like a quick fire round. So maybe just like a few word answer from each. I wanted to know, so for each of you study different modalities and also different developmental periods and different phylogenetic kind of trees as well. So for your field in particular, what do you think changes the most in that evolutionary period or developmental period? So what feature of the gradient or what gradient varies the most for your field? Anyone want to go first? There was a lot of chat in the chat about what changes the most over development. So I know, Jake, you were doing some stuff on development. Do you have any comments on which one do you think is changing the most?
Yeah, but I think what I was doing is a bit different from some of this other stuff because it incorporates kind of the subcortex and the brainstem, whereas a lot of the other stuff is more cortical. And I think that is like such a highly divergent, like there's a lot of divergent stuff going on there. And that's for sure the most salient feature, both in the developmental sense, but also in even after that. But I wonder if that would be probably fairly similar if some of these other approaches, I know it's not really, you can't really get functional connectivity from, those regions very easily, but I would wonder if that would be similar if you did incorporate them, or even just subcortical to cortical.
Sophie, maybe?
Yeah, I was thinking because I used to have also the gradient of aging in covariance in there. There you also saw that the principal gradient of aging was this posterior to anterior region, which also relates to Daniel's hierarchy. So it might be that this is not for nothing the dominant gradient in humans, and that the sequence of gradients that you see also tells us something about what is the mode of the most relevant variance to what you're studying. But yeah,
so quite a strong stability of the different gradients.
Yeah, only when you can kill it when you remove the distance effect. But I guess, yeah, to me this posterior anterior gradient is also like, well, it has to do also with cell divisions and development. So there's a lot to it, especially, well, we had this debate, where's the best apex of the gradient, right? And you were all into the limbic system, and I was a bit more into the frontal cortex. But I do think there's a lot to it, to my view. No, but yeah. As for change and as for like what is special during development in humans, I think the frontal cortex is also quite a cool hotspot.
John, did you have anything to say on that? I know you've also done a lot on transcriptomics, so have you been able to see whether the gradients you're seeing there are also changing across EBER-DEBER?
Is that a question for me? Sorry.
Yeah, well, I know you've just done a lot on the transcriptome.
Yeah, so I mean, I think there's a lot more to understand about what's common and not between species, right? So for example, we had seen this relationship in human between genes correlating with the T1, T2 myelin map. In a collaboration with Ben Fulcher, we looked at that in mouse data, and we found, but for kind of ortholog genes, the degree to it, the correlation of a mouse gene with the mouse T1, T2 map was, that strength of correlation was in itself related to the correlation between the human gene and the human T1, T2. And so it seemed that not only was there a shared common gradient between them, but on a gene by gene level, there were a lot of common genes contributing in the same way to those two gradients across species. And so I think that, but some genes didn't agree. And so it's not clear whether those are technical differences, or I think there's a lot of work to understand to what degree these, not only they're shared and kind of homologous patterns, as Ting nicely showed, but to what degree those are actually supported by similar molecular gradients, or where you may get species-specific dependencies.
Yeah, excellent. Ting, did you have anything to add there?
Yeah, I want to add one point is, it's interesting to see the order of the gradients actually change. So for example, in human adults' brain, we always see this hierarchy gradient dominance, the pattern. But for example, Boris Lab found this gradient in neonate data, and it's actually from posterior to anterior. That gradient comes around the first. And in macaque, it's not a hierarchy gradient come the first. It's actually the gradients spanning along these unimodal regions comes first. And there's a more than one unimodal, the modality gradients in macaque. And in rodent, it seems like if you imagine that this gradient map in this high dimensional space, in the macaque, it kind of like rotated, and in rodent, it rotated even more. So it's actually very interesting to see maybe in the evolution or in these small animals, it's not really the hierarchy of the gradient dominance, but it's more like they are the information flow spanning around the sensory regions dominates the brain organization.
Boris, do we have to wrap up yet, or do we have time for another question?
You can still keep going. It's fine. It's fine. Yeah, sure.
Okay, great. Because I just saw another question come in from Eduardo, who asked, so is there any work on mutated mice with genetic or structural gradients? I'm not sure if anyone has seen any of this work. So is there a way to kind of manipulate gene expression and then study the effect that has on gradients causally? Has anyone seen any work like that? Sounds really interesting.
So I'm just aware of some work from Alessandro Gozzi's lab in Italy, and they are doing gradients in healthy mice, but they also have some mouse lines that allow for genetic manipulations.
Mm-hmm.
Yeah, I would just echo that. There are some people doing, like, I know that, including Gozzi, I think, is working with autism strains. in my esteem looking at that. So I think that would be a good place to look.
Yeah. So that maybe we should wrap up, unless any other speakers had anything else they wanted to chat about. We're all going to be doing a lot of talks this week, so I want to keep that in mind. So with that, I think I'll just say that like thank you to everyone involved. Thank you especially to Sasha, who's been our event organizer of this as well. You've done the actually, I think. Thank you to all our speakers. Pre-recording everything made this really smooth and just, I think, a really enjoyable experience for everyone and very accessible. To all the organizers, it's been great. And thanks for everyone participating. I did not expect there to be so much conversation in a virtual workshop. This went even wildly better than I could have hoped personally. And there's one other thing. So I've collated all the gradient posters and gradient talks that are going to be happening at OHBM this week. So I'll post that up on Twitter. But feel free, if your name's missed out, just message me and I'll add it to the list as well. Was there anything else anyone wanted to add, Boris?
No, thank you all for your participation. I just second what Casey just said. So thank you to all the speakers, to all the chairs, to the audience. I think it was really engaging and I had a really good morning.
Yeah.
I think maybe the final thing is that there's now also a mailing list for gradient related things. So maybe we can also share it on there, and like any future opportunities that people have, they can share on that list, and just encourage others to sign up to that as well.
Great to see the gradients community burgeoning. Cool. Okay, so thank you everyone. Have a nice night, day, whatever time it is, and enjoy OHBM too.
Bye everyone.
Bye bye.
Bye bye.